Hello, this is Concrete Path. Hello, this is Concrete Path, and today's lecture is the second lecture of influence line diagrams. So, in this lecture, we'll be having ILDs using Muller Breslau principle. Muller Breslau principle. So, what it says that influence line diagram ILD for any stress function. For any stress function, we can have reaction, we can have shear, we can have bending moment. So for any stress function that can be obtained, that is obtained. So you do one thing, you remove that by removing the restraint that offers the function it offers. The function offers that particular function, the restraint it offers, you have to remove that. Then after that, you do one thing, you apply unit displacement. At that point, at that section, at that point, at that location. Let's say at that location. And so at that location and in the direction of that function. So let's have this what it actually means, this statement, what this statement is saying. So let's take the first one. I need that reaction at A. You have the simply support beam AB. I want to say what is the ILD for reaction at A. So it says that you have two supports. One is your A and B. So this is your simply support beam AB, and you do one thing. You remove that restraint that was because of that reaction A. So once you remove that restraint because of A, that means this point it is fixed. This point is not going anywhere. But A is the support A. You remove that support A. Once you remove that support A, so it looks like now this one. Now you do one thing. You apply a unit displacement at this support. From this side, it's fixed. We can say it's having a support. So you are having a support and you are applying a unit displacement. Let's say you applied a unit displacement. So the profile that has formed, it is the ILD of that RA, reaction at A. So this is the profile for reaction at A. In this way, you have the reaction at A. So this point has reached here. So this is our ILD for A. I can show it. So you have to make sure that from the B side that is remains intact. So we can write B remains intact. B support remains intact. You don't have to remove the other supports. You have to only remove the support where you are calculating the reaction. So this is your unit displacement of 1. So this is your ILD for reaction at A, positive. So this is your ILD for reaction at A. Similarly, for the reaction at B, you remove the support B, then apply a unit displacement of 1. So this is our profile for reaction B. So this is our unit 1, and this is our ILD for reaction at B. Now second thing is that, so that's what the statement is. ILD for reaction is obtained by removing that reaction by that support and apply the unit displacement of 1 at that location and in the direction of function. We know that at the support the reaction would be upwards. If loading is downwards, reaction would be upwards. So accordingly, in the direction of reaction, you have to apply unit displacement, and accordingly the profile format would be ILD. The second one is that let's talk about the shear force. You have a simply support beam. And you take any section C. How can you get that shear force at C? So it's saying that you introduce a slider here. How can you remove the restraint because of we want shear C? How can you make that shear 0 here? How can you make the shear 0 here? That means you apply a slider. Here. If you apply a slider, that means the profile format would be, then you apply a unit displacement here. How can you apply a unit displacement here? That means you should make some slider here. We can call it as a slider. That means once you apply a slider in this fashion, that this part we can have. So let's say this is your slider here, and we have this beam now, and we are talking about this point C. This is our point C. Let's say this is our point C. Initially, we need to get the shear force at this point C. So we say you introduce a slider. Let's say this is our slider here, and you now apply shear for this part in the downside, and in this part upwards, such that now if this is your support and this is our support A and support B, let's say this is your support B, and from the side you apply shear of V downwards. So what's going to happen? It's going to in this way. So this part AC is going in this way. Let's say this is AC goes in this way. Now similarly, if this is our reference line, and once it goes up downwards, and you have to go for this one, you have to apply upward shear V. Once this is your support B, you apply a slider shear upwards. So this is our profile for this one, but that's above the reference line. Above the reference line, we have to join that in this way. So then finally we can join. So this is our profile, and after that we can join the two. By a straight line. So this is our profile for shear. This one is negative, this one is positive. This is V. ILD for V shear force at C. You apply a slider, then you apply unit displacement in this way. If this is A, this is C, and this is B, I would say AC, let's say this is C1, C2. I would write AC1 is downwards, and after that C2B is upwards in this fashion. Third one is that of a moment. You need ILD for bending moment at any point C. Let's say this is point C. I need ILD for moment at C. So what the statement is saying that you do one thing, you remove the restraint offered by that function. So if you apply if the function is moment, you remove the restraint offered by that function. So we say that let's introduce one thing that we call as how can you remove the restraint because of moment? How can you remove the moment? At any point? That means you introduce a internal hinge here. If you introduce internal hinge at that point C, that means it can release that moment C. So once you applied a hinge here, let's say this is your internal hinge now. Initially this was your profile, this was A, B, and this was C. And we need to get a moment at C, ILD for moment at C. So it's saying that remove the restraint, remove the moment, and you apply a internal hinge there. That means once you apply remove the moment, then you apply a unit displacement. Now for the moment, moment resistors displacement, that in terms of theta. We talk moment in terms of theta. So you apply a unit rotation, 1 unit rotation. So you apply a unit rotation. So we say, for this case, direction of moment is in this fashion, some PL by 4. So positive moment. So on this section we have in this fashion, and for this section we have in this fashion, and from this side we have in this fashion. So if this is anti-clockwise, this is clockwise. So in this fashion we have to rotate it now. So in this fashion, so we say that now you rotate, now you apply unit displacement. Once you remove that M by internal hinge, after that you have to apply unit displacement, that we have to apply unit rotation. We say that you apply theta 1 plus theta 2, that equals to 1. That's also, and both theta is in direction of, that the statement is saying theta should be in the direction of that function moment, moment function. That's what the Muller Breslau principle is saying, that to get the moment ILD for moment at C, you remove that restraint offered that by the moment at C. You remove that moment by introducing a internal hinge there. Once you introduce the internal hinge, now you rotate the two sides of that. You rotate such that theta 1 plus theta 2 equals 1, and theta should be in the direction of moment. So we got that moment should be in this fashion. For this part, we have to rotate that theta should be also in this direction. If the moment direction is this one, theta direction should be the same, and in this part, theta direction should be this one. So let's take that. We have this one. You introduce this one is your ABC. Now this one is your hinge, internal hinge. Now you rotate this part upwards. You rotate this part. Once you rotate this part about this one, so it would go upwards. It would go in this fashion. It would go in this fashion. What is this? What is this? This is anti-clockwise. So here it should be clockwise. Here it should be clockwise, opposite of that. If this is clockwise, if this is positive bending moment diagram, here the theta should be, this is clockwise, this should be anti-clockwise. So theta should be anti-clockwise. So you rotate that by theta anti-clockwise. How can you, if you have this up to the point C, you rotate this anti-clockwise in this fashion. So it goes in this fashion. So it goes in this fashion. So in this fashion we have to go. So in this fashion we have to go. So let's remove this part now. Let's remove here. So in this part you have to go here. So after that, second part of the beam, that is CB. For that you have to apply moment in this direction. So if this is anti-clockwise, this one should be clockwise. This one should be clockwise. So in this fashion. So for the second part, you have to rotate it in the clockwise. So how can you rotate about this point? So if you rotate it clockwise, that is your clockwise moment, or theta should be clockwise, and you rotate it clockwise. So this is your profile. This is your profile. So that the profile here format is in this fashion. So if this is theta 1, it is anti-clockwise. Theta 2 is clockwise. So we say theta 1 plus theta 2 is equals to 1. So the profile format is your ILD for moment at C. So this is the statement from Muller Breslau principle. Let's go now and solve a few problems. Let's go now and solve a few problems. Let's go for the get the ILD for reaction at A in these problems. Let's say first beam we have an overhang, double overhang beam, and we have support A here. This is our support A. This length is A, L, A. We need to get the what you call as ILD for reaction at A. So I would say this is our reference. This is our reference line, and I would say this is our beam. This is our beam, and support A is here. Support A is this one, and this is some other support, and we have two overhangs. Now we need to do one thing. To get the reaction at A, you remove the support at A. To get the reaction at A, you remove the support at A. You remove the restraint offered by A. Let's remove the point A. Let's remove the support A. So now you apply unit displacement at point A. Unit displacement at point A, because reaction is upwards. So in the direction of reaction, you have to apply a unit displacement of one unit displacement upwards. So once you applied 1 unit displacement, so the profile format would be in this fashion. So this is our profile that has format. So this is the profile. So once you applied a unit displacement of 1 here, if this is 1, that means the profile format would be in this fashion. Let's take a unit one. So I would say in this fashion. But you have to ensure that other support is intact. Where it touches, that means that it is the location of the support. Let's say this is support B. This is the location of support B. That means when the load was at B, your reaction at A is 0. So this is our profile. Now you can say by the similar triangles, now you can get the values of other critical points. You can get the location of other values of other critical points. If this is 1 for the length of L, I would say this is theta. Theta equals to 1 by L. You write tan theta equals to perpendicular base. Tan theta is equals to theta, that is 1 by L. So if I write this is 1 by L, this is also 1 by L. That means for length of A, we have this one A by L, negative. This is positive, and this one would be equals to 1 plus A by L. 1 plus A by L by similar triangles. So this is your ILD for reaction at A. ILD for reaction at A. Now take the second problem. That is we have this one support here. One more support is there, that we have support A. Then after that we have one more support, and after that we have free end. and there is an internal hinge here at a location somewhere here. At point C, we have internal hinge at a distance of A, B. So we need to say what is the reaction, what is the ILD for reaction at A. Let's take that. Let's say this is our reference line, and we need to get the reaction at A. We need to get the reaction at A. So for the reaction at A, so what you have to do, you have to remove the restraint offered by that point A. And once you remove that restraint offered by point A, that means then after that it would be in this fashion. Let's say this one. This is your support 1, support 2. There is internal hinge here. There is one more support here. Let's forget the supports from this side. Let's say this is internal hinge at this point, and we have the support A, and we have the supports from this side. So we have to do one thing. We have to remove this restraint. So once I remove the restraint, then apply unit displacement. So the profile for this part, it would be a triangle. Let's say for the first part, you have a here the unit is one unit displacement, and the profile for this one would be straight line. Now the thing is that because you have internal hinge here, that means you won't go as straight. You won't go as straight line. That means once it reaches in this fashion up to the hinge point, let's remove the up to the hinge point. So up to the C point, it would be this would be the variation. This would be the variation. Up to the point C, this would be the variation. So let's have that variation up to the point C. So this would be the variation. Then after that, since there is a internal hinge here, that means after that we have some support here. Also. This support can't go anywhere. That means the profile should be in this fashion, because you have to ensure that the other two sides are intact. Other two supports are intact. That means they are at the same level initially where they were. So this should be the profile. At the internal hinge, there is some θ1, there is some θ2, so such that the ends are intact. The other two sides are intact. So this should be the profile. So then after that, once that we have this. If we take this member, once it rotates, once the first part rotates in this fashion, that means the other part has to go downwards. So if this is a support somewhere here, and if this part has gone in this fashion, that means the other part also goes downwards. So the profile should be downwards. So the other part of the beam would be in this fashion. So this is our profile, ILD for reaction at A. So I hope that you got this. I hope that you understood what we are doing. So let's say the theta here would be, if I talk about this one, I would say this is some length of L, and this is some length of L. I would say this theta is 1 by L, 1 for length of L, and this one would be equals to 1 plus A by L1. And similarly, by the similar triangles, I would say 1 plus A by L1 is for the length of B, and by the symmetry, I would say this is theta. I would say what is this value of, what should be this value? I would say this value would be equals to, and I don't know the length. Let's say this is some length of C. I would say this would be the ordinate here. Yeah. So this was the ILD for reaction at A. Let's take the third problem, that get the ILD for reaction at A for this beam. That's a cantilever beam. So this is our support A. So the problem is that you have a split support. You have a cantilever beam now. That's fixed from this side. Now there is only one support. To get the reaction at A, you remove the restraint offered by that point. So let's remove that restraint. Once that restraint has been removed, so it is going to fall. Definitely, it's going to fall. Now, how can you show that it gets lifted up? Let's say this was your beam. Now here we have some cantilever. Now, but because it's freely hanging, or we can say it's having only one support. Once you remove that support, then you lift to that point A by unit displacement. That means entire beam gets lifted out by 1 unit. entire beam gets lifted up by 1 unit. So if you show the profile, I would say this would be that ILD. Entire beam gets lifted up by 1 unit. This is your ILD. So if this goes 1 unit, that means the reaction at A for each point, that means if the load is anywhere on the beam, you apply summation of forces in Y equals to 0, you would get at each point reaction A would be 1. Anywhere you apply load, you take any load of, you take any X, let's say, to verify it, let's say you take any location of 1 at a distance of X from A, you say, what should the reaction at A? I would say that would be equals to 1. That would be equals to 1. And the moment, if you say what is the moment here, I would say the moment here would be 1 into X, that's X. So for different values of X, we can have moment variation in this fashion. If the load is here, moment here will be 0, and accordingly the variation would be in this fashion. When the load was at this point, your moment at A is 0. When the load is at point B, your moment at A is some sort of thing. When the value of X is here, that means when the load is at the free end, your moment at the A is maximum. That's X times 1. So similarly for the reaction, you have this variation. Do you got it? Do you got this one? So second problem we can take that's about the reaction at the shear at B. We need to calculate the shear force at B. So second case of problems, we need shear force at particular point B. Let's take that point B. So this is your beam and point B is here. This is point B. So let's take that point B. You have this beam, you have this one. So now you introduce a slider. To get the shear force at B, you introduce a slider. Let's introduce a slider. And on this side, you have apply downward, in the side upward. See, one thing is that the Muller Breslau principle says that if you have statically determinate beam, you join the ordinates. Once you got the critical ordinates, we join. We have ILD using. We draw ILD using straight lines. But if you have indeterminate beam, if we have statically indeterminate beam, we have ILD using curved lines. We already studied also in the first lecture. So for the indeterminate beams, we show by curved lines. In the determinate, we show by straight lines. Now the thing is that if in case of let's say, if because of shear force, moment, or reaction, if somehow in statically determinate beams, let's say this is our statically determinate beams, if in this case somehow curvature got developed, that means that's not true. That means the ILD for that part would be 0. So ILD for that part would be 0. You keep that in note. ILD for that part is 0. If there is if curvature is developed anywhere in the statically determinate beams because of some shear, moment, or reaction, that means curvature should be 0. Curvature gets developed, that means you have to draw ILD for that part 0. Let's have that in this one. So once one is to separate the 2 points, I would say for this one you are applying a shear of 1 downwards, and for this one you are applying a shear of upwards 1. So I would say this is some sort of continuous system. You can assume that this is a fixed side, and you are applying a load of 1. That means the profile would be in this way. Curved profile would get developed. PL cubed by 3EI. That's some sort of that way. So once that curvature has been developed, that means this part is not valid. This part is not true. So this part, so ILD for that part would be 0 line. ILD for that part would be 0 line. Let's keep this part to some side. Let's keep this part to some side. So for this side we have ILD 0. For this part we have ILD 0 because we have there is development of curved nature. Because of this shear here, if you apply shear for this side, curvature gets developed in this part. That's continuous part. there is continuous part, you are applying a load, and it would deflect in this fashion. Let's say I will show you that. You're applying a load of V here, and because of that there is transfer of moment here, 1 into some length of A, and there's some shear also reaction of 1. So remove this one. So because of this one there is development of curvature. So theta, because of theta there is some curvature. So because of curvature it's not possible for determinate beams. So ILD for determinate beams for this part is 0. So we say that ILD for this part is 0. Now that means we are only left with this, the other part that's having this shear. So you are applying a shear of V downwards. So once you cut this section at this point B on the left side, you're applying a shear downwards. So entire part is going downwards by this amount. Entire part is going downwards by this amount, V downwards. So because I would say you have to ensure that V downwards plus V upwards, it's 1. We already know that when you apply the shear force, this was your minus A by L, this was your B by L, such that entire 1 unit was there, such that A plus B, such that A by L plus B by L was equals to 1. But once we know that for this part ILD is 0, once for this part ILD is 0, that means the entire shear of 1 has been used for this part, for the negative downward side. So entire 1 unit gets transferred to this part. So I can show entire, I would take that, I would say this entire 1 is applied on this part. So a shear force diagram, ILD for shear force diagram would be in this fashion, minus 1 up to this point B. So this is your ILD for shear force, ILD for shear force at point B. So if you want to still you can check it, because we have studied in the first lecture. You can do free body diagrams, and you can check what is the shear force diagram nature variation in this beam. You can still check that one also. But based on the Muller Breslau principle, this is our profile. This is how our profile looks like. Now let's take the second problem for the reaction at B, shear at B. So second one is that you have this one, after that this one, and after that you have this one. So let's say this is some support B. Let's say this is some section B. We need to get the ILD for shear force at B. This is our section at B. Let's say this is some length of B. This is A, this is D, this is C, and there's some internal hinge here. Internal hinge, so it can allow theta. So this is our beam. So we need to get the shear force at B. Shear force at B. So what it says, you introduce a slider. Let's introduce a slider. I would say there is some slider, and in this side we are applying downwards, and in this side we are applying upwards. So, but here we have some internal hinge. Let's say that this part, if we talk about this part, it is similar to that of a simply support beam. This part is similar to that of a simply support beam. You can check that also by, if you have two pens, you can check that now, shear force. So for this part, you have a support here. Once you try to lift this part, once you try to lift this at this point, at point B, this is your support at this other side. So once you try to lift this one by some shear of upward, I don't know the value of shear upward, so let's say some shear is applied, and from this side you have to keep that in intact condition. So this is our profile for this side. So this is our profile. So for this part, we say the profile would be in this way. So this is our profile, that's positive. After that, if you talk about this one, I would say you keep this support intact. Now you apply a shear downwards. So this is our profile for this one. You apply shear force, and this is our profile for this one. Now you join them, and this is negative, this is positive. ILD for shear force at B. Now talking about the other part of the beam, so we have some internal hinge at this location, and we have some fixed side here. So we need to say what is the variation here. Let's take that part now. So once we got that, because of that, once we say, let's call it as, to get the understanding, let's say this is X, Y, Z. xyz into this is alpha. So once alpha has gone down, and at the support, let's say this is some support, let's say this is some support z, let's say this is some support z, and alpha has gone down, that this support z has to remain at the location of z itself. It won't go anywhere. So z is here. But if you talk about that up to the point y is here at the internal hinge. So remove that other part of that xy. So point y has reached up with respect to the main line. With respect to the main line, z is here at the support itself. So with respect to the main line, y would go upwards. So this is our profile, that y goes upwards. So there is a variation. So this is positive. And after that, because support x won't go anywhere, now once it has reached, y has reached here, there we have some support x, and there we have some internal hinge also. Internal hinge can allow independent rotation of those two members. So let's say this would be the profile. Final profile would be in this fashion, such that your support z and support x are at the same level, or they are at the same level. You have to ensure that support x and support z are at the same level, initial level. So this is our profile. Now join the two, and this is your ILD for shear force at B. In the previous problem, can you see the difference in the previous problem and with this, in the previous problem and with this? If you compare the other problem with this one, can you compare the two? If you compare the two, so in the previous problem, here there was no support, and once you applied shear of downward 1 unit, and entire part of the beam goes downwards by unit of 1. But in this one, once you applied that shear of 1 unit, let's say some unit of V applied here, but we have some variation of linear because your support is there. If it was in this fashion, so it would have gone upwards by same amount of some shear force V upwards. So entire would have been positive. But because your support is there, you have to remain there. You have to keep that intact position. So your variation is in this fashion. Now coming for this part, in the previous problem we say, because of this shear, it is similar to that of a cantilever. You are applying a shear, so there would be a curvature developed. So for this part, there would have been a curvature that has got developed in this fashion, some sort of maybe some sort of in this fashion, curvature would have been developed. So for that, I would say withdraw 0 ILD. Now for this case, it is similar to that. If you compare this part, it is similar to that. Let us show that. So this part is similar to that of that previous one, but the difference here is because of internal hinge, there is a change. So that we can check here. So you are applying shear here, you have a support here, you have an internal hinge here. Once you apply a shear of V here, that means let us go and apply shear of V here. Let's apply shear of V here. That means this part goes upwards, but because of internal hinge, it can allow rotation. Once it can allow rotation, that means there is a possibility that they can rotate. And ensuring that the supports are at the same level. So this was the profile. Finally, this was the profile. But in the previous problem, there was no internal hinge here. Let's say there was no internal hinge. Now you have to ensure that once you apply shear force of V here, and we have two supports. Let's say this is one support and this is one support. You are applying a shear of V here. Let's say that this goes downwards. And B, this support Z is at the same level. But if you compare this support X, that has gone upwards. But you have to ensure that support X has to remain at its own location. So that means there would be a bending developed here. Curvature would get developed here. So that's not possible. That's why we have ILD of 0 in the previous problem. Okay. Let's take the third problem of shear. So we need to get the shear force at B for this condition that if you have a cantilever beam and this is your section B, and we need to get the ILD for section shear force at B. So let's introduce a slider. I would say this is your slider. This is your slider, not guided roller. This is your slider. It can allow vertical delta. So next one is that guided roller. We call that as guided roller. That can allow downward vertical displacement, but it won't allow theta. So let's say there's some v downwards, and in this side we have v upwards. So let's talk about this one. You're applying a shear of v downwards, and there's some cantilever, and you are applying shear. We know that deflection would be curved. If the deflection forward would be curved, that means ILD would be 0 for this part. That means this shear would be 0, because this is not possible. If this is not possible, that means entire shear of 1 unit has been transferred to the other side. That means entire shear of 1 unit has been transferred for this side. Now for this side there is no support from this side. You are applying a shear of 1 unit upwards. So once you apply the shear of 1 unit, entire section gets upwards by same amount. So this is our profile. So finally I would say the ILD would be 0 for this one, and after that once it reaches B, then we have upward 1 unit, positive 1 unit. So this is your ILD for shear force at B variation. Hope you got that. And you can check that also by using the analysis of ILD. We have performed that in first lecture also. You can do that way. That way also you can do. So let's take that. Now third problem is that you need to get the moment at particular B on these problems. Let's take the first problem, and we have simply support. After that one more, and then after that we have point B. This is your section B, and we need to get the moment at B. So for the moment B, we say you introduce internal hinge. How can you remove the restraint of moment? That means you introduce internal hinge. Let's introduce internal hinge here. This is internal hinge here. Okay. Then after that you apply unit rotation. θ1 plus θ2 equals to 1 unit. You apply rotation of θ1 plus θ2 equals to 1 unit in the direction of moment. So let's say that in this part there was some load. So that means moment developed would have been hogging. Hogging moment would have been developed. That means theta would have been in this fashion. So in the same way, let's say that this was your section, and you have to rotate that in the theta in that way. So we say that this is your section. We say that moment is anti-clockwise, negative hogging. So we apply rotation in the anti-clockwise direction. This was your moment. We apply moment in the same direction. So let's say that because here the moment is negative, so we say let's apply a rotation of in this way. Let's apply in this way rotation, negative moment. So apply rotation of, let's say this is, you're applying θ1 and θ2. So once you separate the two, let's analyze the two. So you're trying to rotate this part in this way, and you're trying to rotate this part in this way. Now what's going to happen? For the first case, we see that there is some apply. Let's assume that there is some moment. And you are applying moment of m in this way. So we know that there is development of curvature. Development of curvature is possible, isn't it? Can we say that moment curvature would be developed? Let's say moment, some sort of curvature get developed in this fashion. Let's say in this fashion curvature might get developed. So since there is curvature developed, so we say ILD for this part would be 0 because of this one. So θ1 would contribute 0. So I would say θ1 would be 0 because I would write because ILD for the first part would be 0. So that means θ2 would be entire 1 unit. So you have to rotate that other part of the member by unit of 1. So you have to rotate this part by an amount of 1. So once you have this part and you want to rotate it clockwise, unit of 1, that means the profile format would be in this way. So a unit by rotation of 1 unit, that means the profile format would be in this way. And for this part we have ILD 0 because if there was some theta in this part, If there was some moment, it would form a curvature of their beam. But we say that for the ILD, if there is curvature in the statically determined beam, ILD would be 0. ILD would be 0. So for this part, ILD is 0. So ILD is 0 for this part. After that, we say there is a downward rotation. We can say the theta developed here is theta equals to 1, or we can write theta 2 equals to 1. Once you applied a unit rotation of 1, and we have some length of, let's say this is some length of A, I would say the value of the ordinate here would be developed. The ordinate developed here would be equals to, this would be also A. If this is length of A, I would say tan theta equals to theta equals to perpendicular by base. That is perpendicular by base. That's perpendicular is also A. So once you rotate it 1, same amount of ordinate is formed as that of length. So you have to keep that also in mind. So let's take the second one. Let's take the second one. So we have this one. A, there is some section B, A, B, there is some support C. After that we have hinge at D. After that we have support E. Let's say this is CD. So we need to get the ILD for moment at B. So what we have to do? Remove the restraint offered by that moment function. That means you have to apply a internal hinge here. Once you apply the internal hinge here, initially there was one internal hinge. Here we have support. Here we have support. So this is your internal hinge here at this location. And we know that the bending moment diagram is in this fashion, PL by 4 positive. So in this fashion, positive. That means in this part, if this is clockwise, so in this part it is anti-clockwise. And in the other part, so if this was what you call as clockwise, anti-clockwise, so here it would be clockwise theta. So M will be in this fashion, M would be in this fashion, M1, M2, but M1 and M2 would be same. Let's say there is some theta 1, there is some theta 2. So we have to rotate it in this fashion. So for the first part, you have to rotate upwards. So in this fashion, and in this one, you have to rotate in this fashion. So once you rotate this one, you have this internal hinge. You rotate this part upwards, and you rotate also this part with respect to this clockwise, so it would go in this fashion. You try to rotate yourself also, and you would be receiving this profile. And I would say the profile format would be in this fashion. Up to this part, we have to ensure that other supports are intact. So there we have 0. After that, now to maintain the continuity of that member BCD, we see once your point B has reached, let's say this was your support A. Once point B has reached here, and this is point B. Let's say this is point B, and this is point C here. Once point C has reached here, now the thing is that there is point C. After that point C, there is point D. Here we have internal hinge. At the point D, we have internal hinge. So that means the profile of CD would be downwards. Profile CD would be downwards. Up to the point that where we have internal hinge, and we have to ensure that this point is at this location because we have support here. That means we have to ensure that there is support at the location of itself. Then after that, at the point D, we have internal hinge. See, once we have internal hinge here, let's say this is at point D, we have internal hinge, and CD has gone down in this fashion, but C is at the location of itself. It intact, C is intact, D is here, and support E, we have to make sure support E is also at its original position. So I would say the profile would be in this fashion. CDE would be in this fashion, such that support C and support E are at the same level initially where they were. So let's have that variation also. So this would be the variation of that what you call as ILD for moment at B. So you can also calculate those values. I would say this value would be equals to AB by L. Do you know that? This value would be equals to AB by L. This is positive, and this value would be equals to by the similar triangles. I would say that AB by L is for the length of, so I would say AB by L, this value is for the length of B, it's per length of B. If I needed, because theta is same, if I say what is this ordinate, I would say this ordinate would be equals to this one for the length of B, but I need for the length of C, so you have to multiply this C also, so you get this ordinate here, and this one is negative, top one is positive. So you got the ILD for moment at B. Let's take the third one, that you have a cantilever. This is your section B. I need to get the moment at B. So you can do one thing, you introduce internal hinge. Let's introduce internal hinge here, ILD for moment at B. Introduce an internal hinge here because the moment is anti-clockwise, minus times BL. You apply load anywhere, so moment would be anti-clockwise. So for this case, if you apply unit of 1, and in this case you apply unit of, this is clockwise, this is anti-clockwise. So this is the variation. So in this case you apply in this way, and in this case that means negative moment. So for this case, once we have a cantilever, you're applying a moment of M, it would get a curvature developed. So ILD would be 0 for this part. So this is the general thing, that if the curvature gets developed in the statically determinate beam, the ILD for that part would be 0. And for the next part we have theta clockwise. So this is your theta developed, theta 2 equals to 1. That is 1 unit of rotation, because theta 1 is 0, because there is no possibility of that. Once it gets developed, a curved nature is developed. So we say that ILD has to be 0. That means theta would have been 0, theta 1, and similarly theta would be equals to 1, such that if this is length of A and this is ordinate of A. So this is your profile, that bending moment variation. I can show that this is the variation. Unit of 1, this is minus, this is A, this is A. This is the ILD for bending moment at B. So now the thing is that, what is the use of ILD? What is the use of ILD? So you see these results. What is the use of these ILDs we have? What is the use of these? Let's see this one. Let's take this one. Let's take this one. What is the ILD? Let's say, what is the use of ILD? You write what is the use of ILD. So from this one you can see, by moving the unit load along the length, we see that if the load is, this is for the bending moment at A. ILD for bending moment at A. We see, if you move the load from this point up to this point, you see that if the load was here, the moment developed at this support was 0. If the load was here, the moment developed is equals to x into 1. That's x meter units. That means by applying a unit of one unit load, your ordinate here is some sort of x. Now if you apply a particular load of 100 kilonewton, I would tell that what should be the maximum bending moment we can have at support A. What's the maximum bending moment we can have at the support A? That is, if you have this ordinate, maximum ordinate, I can write maximum ordinate into multiply of that load of P. So I can write that 100 kilonewton into that ordinate of x meter. Let's say the x meter is 2 meter. So you can get that maximum maximum moment we can have on this beam, that is 200 kilonewton meter. Once you got the maximum bending moment, I can say you have some section of BD square, then you have BD square by 6 section modulus. Accordingly, you can design the material which is having some permissible stresses. There we have some sigma into BD square by 6, so that's your moment. So we say that the moment of resistance should be more than the moment that's 200 kilonewton. Accordingly, you can design the section. So this is the use of that ILD. So let's take the problem. Let's take the problems now. Let's say we reach it here. Let's try. We also solved this one also. Let's keep this on the side. And we need to get reaction A, shear B, moment B. We need to get reaction A, shear B, moment B. We have a beam. We have a beam. We have a beam here. And we need to get reaction at A, shear at A, moment at B. So this is D, this is A, this is what you call as B, and this is C, this is E. And we need to get that reaction at A, shear at A, moment at B. Shear at B, we call it as shear at B. So let's write the dimensions also. Let's show the dimensions. We say this is E, this is A, this is B, this is F. Now up to this point, this is length of E, this is length of A, this is length of B, this is length of F. So let's apply the Muller Breslau principle. Let's go for the ILD for reaction at A. ILD for reaction at A. ILD for reaction at A. So we have this beam. So we have a simply support beam with two overhangs. So there we have supports at A and C. Now what the problem is saying? Get the reaction at C, reaction at A. So reaction at A, go for that. We say remove the restraint offered by the reaction at A. Remove the restraint, okay. Then apply unit displacement while keeping the other supports intact. So this is your support C, that's intact. Now you apply unit rotation. This one is not internal hinge. At the point B, this is not internal hinge. Okay, you apply unit rotation, but you have to ensure that point B is at its location. So this would be the profile. This would be the profile. And point B is on the that main line. Point B is on the main line. So you have to ensure that point support C. So let's have that. Let's have that variation. Let's have that. I would say point C is at its location, and there is a variation in this fashion. So this would be your ILD for reaction at A. So I would write the values. So I have to apply at point A unit displacement 1. If this is 1 for the length of A plus B, let's say L equals to A plus B. If this is L equals to A plus B, I would say this is theta. This is 1 by A plus B. Theta equals to 1 by A plus B. And that means this one is equals to 1 plus, and this length of E by A plus B by similar triangles. This is the value here we can have. That is, I can show that. I would say we have bigger triangle. We don't know this ordinate. And we have this length of that A plus B plus E. We have this ordinate of A plus B plus E, and theta we know. Theta is same 1 by A plus B. So I can write theta equals to, this is theta. This equals to some ordinate of P divided by length of perpendicular by base. So you got this one. Here we have this one also. That is 1 plus E by A plus B. So you can also get A plus B plus E by A plus B. That's L plus E by L. So you got this one. And this is a positive ordinate. And after that, similarly, we can say this is your theta same. If the theta is same, we can write this one also, that this is a value of that F by A plus B. This is a theta. We can write theta equals to perpendicular by base. That is equals to some perpendicular by base of F. So you can get the P equals to F by A plus B. So you got the reaction at A. Now we need to get the reaction at shear at B. Let's remove this part now. Shear at B, shear at B, shear at B. We need to get the shear force at B. ILD for shear force at B. So for that you have to apply what? A slider. You have to apply a slider here. Let's apply a slider here. And in this part you have to apply downward shear, and in the next part you have to apply upward shear. So we have these beams, we have two supports A and C. Now it's saying that you apply at the point B, you apply shear downwards. So for this part, this would be where profile, and for this part you have to apply shear of upwards. So this way. So this would be profile. That for this one it goes downwards. So this would be profile. This would be the profile. But you have to ensure that support A and support C are intact, that means they are at the same level, and this would be the profile. If you have these, this would be the profile. This is the section B. This is the section B. So you have to show that they are at the same level but inclined. So this is the variation. But you have to ensure that support A and support C are at the same level. This is the profile. This is the profile. This is the profile. Let's go for the profile. You have to ensure that this is intact, this is intact, but this one goes down and this goes up. And similarly, this one is parallel, this one is parallel. So in this fashion, we can have this one, that this is parallel and this is also parallel. So we can show the variation in this fashion. So this is your what you can call as shear ILD for shear force at B. Now I can get the values. I know the values directly. We know that the values are this is the total unit of 1. This is the total unit of 1, and I know that ordinate is bottom ordinate is minus times A by L minus A by L. This one is B by L, where your L is A plus B. So you got this one, and by the symmetry I can say, by the symmetry I would say what's this ordinate? I would say we have this B by A plus B. If the theta is same, I would say this is for the length of B, but I need for the length of F. So you got this ordinate. And from the other side, we can say we have this ordinate. We need to get this ordinate. I would say this ordinate, because theta is same from the two sides, I would say A by A plus B. It was for the length of A, but I need for the length of E. So this is E by A plus B. That's E by L. So we got the shear force now. Now we need to get the bending moment at B. Bending moment for B. ILD for bending moment at B. Let's have that one also. ILD for bending moment at B. So Muller Breslau principle, use that. It says to get the stress function of moment, you remove the restraint offered by that moment function. So you need to remove the restraint offered by that moment function. How can you remove the restraint? So that means you introduce an internal hinge here, and then you apply unit displacement of unit rotation of theta 1 plus theta 2 equals to 1, and that theta should be in the direction of movement. If there we have moment of clockwise moment positive, because moment is positive, so this is our variation. And in the part A to B, we have moment, this is clockwise, this is anti-clockwise theta m, and theta we should have theta 1 in the same direction. And for the part B, for the part CB, your moment should be, if this is what you call as anti-clockwise, here the moment should be anti-clockwise in this fashion, and the theta 2 should be in this way. So finally we say that the variation would be in this way, that you go in this way, you go in this way, you go in this way. And this, we know this is maximum ordinate. We have AB by L, AB by L. We already know that. So once you have this support, you rotate it clockwise. So this goes up, this goes up in this fashion. And we have the support C, and you rotate it anti-clockwise. So this goes up also. So this is the variation. Then you directly know, when you do a little bit of practice, you already directly calculate those values. You already know what is the nature. So if you say this is your simply support beam, and you want to say what is the moment here, I would say this is your AB by L. Directly you can say, or ILD would be AB by L for this one. So this is the ordinate. Now once your support A is here and support C is here, so that means once support A has gone in this fashion, that means the overhang would be downwards. And similarly for the support C is here, and ordinate CE would be downwards with respect to that point C. So in this fashion we can have. So this would be a variation of that overhang also. So I would say the ordinate here would be negative, and this ordinate would be, this was your AB by L for the length of A. I need for the length of E, that's BE by L. That's BE by L. And this one, this was your AB by L for the length of B, but I need for the length of F. So this is your BF by L, AF by L actually. So it's AF by L, AF by L. So this one is positive and this one is negative. ILD for moment at B. So let's take one more problem. Let's take one more problem. Let's take one more. Let's take one more. Let's take one more. Let's go for a second. Let's go for a second problem. Let's take one more problem. We have support A. We have 6 meter. We have support B. We have 3 meter. We have internal hinge. Then we have simply support, roller support C. This is 3 meter. And we need to get reaction A, reaction B, reaction C, moment B. Reaction at A, reaction at B, reaction at C, moment at B. So let's have the reaction at A. We say you remove the restraint at A. Let's have the line. Let's try that this is ILD for reaction at A. So we say here you remove the restraint at A, apply unit displacement upwards because reaction would be upwards. Then after that, you keep the other supports intact such that if this is intact, that means you join them by a straight line. After that, if there was no internal hinge, that means the profile would have been in this fashion. But because that means there would have been a curved nature, because point C won't go down. Points, you have to ensure that point C is there. Let's say there was no internal hinge. Let's have that analysis here. We say support, this is point B, this is A, this is support B, this is internal hinge at D, this is support C. So we have this internal hinge at C, internal hinge at D. So you have the support. You do one thing. This is support B, this is support A. You apply unit rotation at this point A. So the profile format would have been the ILD, but once it goes in this fashion, okay, support B we kept intact, and we have to ensure that this support is also intact at the location. The support C should have been here if there was no internal hinge. So that means how can you show that the support C remains at that intact? That means there should have been bending of this part BC, because there is no point D, because there is no internal hinge. So BC would have been some curved nature such that B and C are at the same level in this fashion. So there would have been a curvature developed. So if point B was here, let's say that keep that also in note. We say if there was no hinge at D, so that means you should have to keep support B intact, support C also intact. That means the profile should have been in this fashion. The curvature would have been developed, but the case was so the profile would have been in this way, and that's true for the statically indeterminate structure, and that was true if there was no hinge here. It would have been statically indeterminate structure. You can see that. This was your statically indeterminate structure, and the profile would have been here in this fashion, some sort of in this fashion maybe. So accordingly we got that that deflection profile would have been in this way. Accordingly we should say that shear force, that ILD for reaction aid would have been in this way. Now because we have internal hinge, we have one more condition, so such that structure is statically determinate. So let's analyze that now. So we got this part. Let's remove this part now. Let's keep it down. I would say once you lifted that point A upwards 1 unit, then you make sure that point B is intact. After that, let's have that analysis. Support A, support B, internal hinge, support C. Now you do one thing. You lift that point A upwards. Okay. So point B is intact. Now from point B to point D up to hinge, this would be the profile. Point B to point D. But after that, you have to ensure that point C is intact at the support location. That means this point B and point C are at the same level. So the profile would be in this fashion, such that there is some theta independent at the hinge. theta 1 and theta 2, they can have any theta such that you have to ensure that B and C, they are at the same level. So this way, this is the profile. This is the profile we can have. Let's have that profile. Let's have that profile. So this would be the profile. Negative, positive. So this was your reaction at A. Reaction at A. ILD for reaction at A. Now the ordinates would be, this is 1, 0, and if I say what is this theta, I would say this is theta 1 for the length of 6. Length equals to 6 meters, so 1 by 6. So this is also 1 by 6. I would say for 3 meter we can have this ordinate of 0.5. Can you say that this ordinate is 0.5 by the symmetry? This is ordinate of 0.5. Now for the reaction at B, we need to get the reaction at B now. Let's go for the reaction at B. Reaction at B. So let's say this is our reference line, and we need to go for the reaction at B. So at the point B, to get this ILD for the any stress function, that is reaction at B, you remove the restraint because of that offered by the reaction B. So we say this is the restraint offered by the reaction B. So we remove the support at B, then you apply unit displacement in the direction of reaction. So this is your unit of 1. Let's say this is a unit of 1. Then after that, you keep the other supports intact. Once you keep this support A intact, that means the profile would be in this fashion. After that, because there is a continuity of BD and there is an internal hinge also. So once there we have this B, A, B, internal hinge D, there we have support C. So we say you apply rotation, you apply unit displacement upwards of unit 1 at point B. So this is your profile. So support B is there, but the thing is that B, this is B and D, they gone up. So BD goes up. Now the thing is that you have to ensure that C is also intact. That means C should be at the location of A. That means the profile would be in this fashion. So this is the variation. This is the ILD. So we can get the ordinate also. I would say this is your theta 1 for the length of 6, and this is the length of 9. So I would say this is 1 per length of 6, and I need for the length of 9. So this is 1.5. Or we can also say 1 plus some ordinate of 3 by 6. That's also 1.5. And this is 0. So this is positive ILD for reaction at B. Now third one is that reaction at C. Let's say this is our reference line. Now you apply unit displacement at that point A, point C. This is 1 unit. After that, let's have that now from this side, because we have internal hinge here. Support A, support B, internal hinge D, support C. So what we are saying, let's forget about point A now. We have support B here, internal hinge, support C. So support C, for the reaction at C, you remove the support C, apply unit displacement. So once you apply the unit displacement, so this is the profile. So the profile is in this fashion. Now up to the point D, there is no change. The profile is as it is. Up to the point D, profile is as it is. Profile is same. But the thing is that you have to ensure that, let me see the variation. You have to ensure that let's say the variation is somewhat in this fashion. We have to ensure that support B is at its location, and support D is also at its location. Now see the thing is that now variation is in this fashion. So variation is in this fashion downwards. Now we need to see how is the variation. Where should it cut? This is the concern. let's keep the arrow here somewhere, because there might be a confusion. So at the support D, if you go in this fashion, okay, if you go up to this point in this fashion, after that, how can you get this one? So let's have analysis of this one, because it might get confusing. You might get confused in this one. So I would say, if the load is in this part, if the load is at support C, you would get a unit of 1. If the load is here, at the hinge itself, so you would get a reaction of 0 here. Reaction C would be 0. That means you can treat this internal hinge as a simple support. That means this is a beam of simple support RC, and there is a support RD, and you apply unit displacement here such that finally it becomes 0 here. So this is the profile here. Because of this one, you can see from the free body diagram, if the load is just at point D, your reaction at C is 0. Similarly, if the load is somewhere here, and there might be some shear force at D, but the reaction at C would be 0. For all shear forces of V at D, your reaction at C becomes 0. That means for all lengths, for all values of X in this part, if the load is in this part anywhere, your reaction at C becomes 0 because of this free body diagram. Let's say there is some shear force at D, but by the summation of moments at that point D equals to 0, so you would get a reaction C into some length of 3, that is 0. So reaction C is 0. So that means the profile would be a linear profile in this fashion. So the profile would be, let's remove this one. So the profile would be up to the point D, you have to show that it becomes 0. This is 0, 0, and this is 1. So this is the variation that it should go in this way. But support A has to remain intact. Support A has to remain intact. Support B has also to remain intact. And if this was the variation, that means see the variation. If this is the variation, now we can say CD goes downwards in this fashion. Now to maintain the slope, we say, let's say that internal hinge would allow rotation of θ1, θ2 such that support B is at its location. Okay, see the conclusion now. Variation should have been in this fashion. You apply unit load of 1 upwards, so in this fashion would have been variation, but there is internal hinge here. Let's see that. But we have to ensure that B and A are at the initial location where they were originally. So once this goes downwards in this fashion, point B has to remain at the location of initial location of A, at the location of initial location of B. Now if this is the variation, okay, we say that support A has gone upwards. Okay, no problem. Support C has gone upwards. Okay, support hinge has also gone downwards. Okay, no problem. And we say that after support B has reached that is at its original location. Okay, but what about the support A? If this was the variation, what about the support A? You ensured that support B is at this location. Support A has gone upwards. That is not possible. That means there should be some curvature developed in this part such that support B and support A are at the same level. So there would be some curvature developed in this part, in this fashion, such that support A and support B are at the same level. So that means for this part ILD is not possible. So finally this variation is only possible up to the point D, hinge point. Since we say if there is little bit of theta in this part, if there is some little bit of theta in this part, if we say that there is some theta in this part, if there is even a little bit of theta in this part, that means there should be definitely some theta in this part, such that A has reached upwards. Now to ensure that the support A is not there, so we say there is some curvature. So if there is the curvature, that means ILD would be 0 in this part. And we already have shown you that by the free body diagram, that once the load is just to the left of D, your reaction at C is 0. Okay. So this was a critical problem here. This was a critical one. Reaction C. Now we need to get the moment at B. We need to get the moment at B. 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 So this is your support. This is reference line. And we need to get the moment at B. What the moment at B says? Remove the restraint offered by the moment that function. So that means you apply a internal hinge here, and there we have support. There we have support. There we have internal hinge also. Now the thing is that if we do it in that of a problem, say if this is your simply support beam, load is anywhere in this part. Load is anywhere in this part. Can you tell me what is the moment here? What is the moment at B? I say moment at B is 0 for this part. If the load is just to the left of the point B, react support B, your moment would be 0 for all cases. So for these cases, moment would be 0. That means for this part, your ILD would be 0. ILD would be 0 for this part up to this point. ILD would be 0 for this part. That means theta 1 would be 0. Theta 1 would be 0. So if you apply some theta here, if you apply some theta here, theta, I would say theta 1 would be equals to 0. Now we are left with only theta 2. Theta 2 would not be 0. Now theta 2 would be equals to 1. So theta 2 would be equals to 1. Theta 2 equals to 1. Now you can also check that by this condition. Now let's assume that for the part AB is a statically determinate part. Okay. Now let's say you are applied some moment M. What's going to happen with that M? What is the profile it can have because of this moment M? Would there be a curvature developed? Do you think that curvature gets developed? Here we have ML by 3 EI. Here we have ML by 6 EI. So a curvature gets developed. We have theta, we have curvature also. So we say that for this part, if there is, even this is a statically determinate beam, if there is curvature developed for the part, so we say this part takes ILD of 0. That means theta 1 should be 0, such that theta 2 is entirely taken by that other part of that BD. We can call that BD. Now we have two internal hinges. Let's say we have this hinge, and we have one more hinge. After that, we have support C. Now you are applying a theta of let's say that you are applying a theta of the theta should be opposite. The theta should be in the clockwise manner. Theta should be in this fashion. Theta should be clockwise. This one is anti-clockwise. So this is the variation of theta. So this should be the variation of theta. Now the thing is that theta should be in this fashion. Okay. So this is hinge, and this is support C. Once you apply theta in this fashion, say in this fashion, so this would be the variation, but you have to ensure that support C is at the location of support C itself. So this would be the variation, and from this side there is a straight line variation, and this would be your final ILD for that moment at B in this fashion. This would be your moment at what you call as moment at B. This would be your rotation, final ILD. Let's make that now. Let's make that. I would say for this part, because your curvature gets developed because of some theta, but in this part we can have some theta. That theta equals to 1, and I would say if this is length of 3, can you tell me what is the ordinate here we can have? It's also 3, and from the side by the symmetry, this is also 3 meters, so this one is also 3, so this is also theta equals to 1. So we have this ILD for moment at B. This is the ILD for moment at B. That means if you apply load, that's similar. We already have the conclusion that once we have simply support beam, load is here. That's entirely taken by this one and this one, such that moment here is 0. So there is no load here anywhere. So we say that is simply support beam, and moment here is 0. Moment at B is 0 for all values of this x. So that's why we say for all values of x up to this point, your moment at B would be 0. For all values of x, anywhere you take the point load, unit load, you would have a moment of 0 up to this point. But as long as it reaches somewhere here, we can have some moment of some theta moment of p into l anti-clockwise in this fashion. In this fashion, we can have moment about this point. So that's why theta here developed is in the same direction. Because if the load is here somewhere, the moment developed would be in this fashion about the point B. So that's why we write the theta in this fashion. So you got this one. Up to the point C, so this is the variation, and if the load is somewhere here, and that gets some sort of, let's say it was somewhere at this part of that 1.5, 1.5. That means out of that 1, your shear force would have been here 0.5. Same 0.5 would be transferred to this point, and after that, we can have a linear variation because of that in this one. Hope you got that. Hope you got that. Hope you enjoyed that. Let's take that one more problem. Let's take that one more problem. Let's take that one more problem. Let's take that what we call as a beam A, D, C, E, B, 2, 1, 2, 2. We have this D, we have this hinge C, we have this E. We need to get reaction A, reaction B, moment at A. Reaction at A, reaction at B, moment at A, ILD for these stress functions, ILD. Get the ILD for these three. So for the A, do you know that if you have cantilever beam, and you apply any load, you apply a load anywhere, so reaction at A would be in this fashion, because you lifted that point A, one unit, entire thing gets lifted up by 1 unit. Do you know that? Do you have that concept? Entire thing gets lifted up by 1 unit, because there is no support from this side. Once one is lifted this part, so the entire thing gets lifted up. Okay. Let's have that analysis here. Reaction at A. Let's say this is a reference line. Reference line. This is a reference line. Now what you do? One thing. You apply a unit load of. No, you remove the restraint offered by that ILD for reaction at A. You remove the restraint offered by that reaction. So this then apply unit load of unit displacement of 1 in the upward direction, because your reaction would be developed upwards if the load was acting downwards. So I would say this is your 1. After that, up to the point C, let's have that analysis here. So hinge is C, this is C. Okay, this is C, this is support A, this is what you call as simple support B, and this is your fixed end A, C, B. What you can do, the problem says remove the restraint offered by the support A. Okay, now the thing is that you remove that what you call as you lift the entire thing by 1 unit. You lift this by 1 unit. When you lift this entire thing by 1 unit, let's assume that there was no what you call as support B. So for at this cantilever, at this hinge point, it can allow rotation. So if you remove that hinge for now, I would say you lift this part by 1 unit. But you have to ensure that point B is at its original location. So to maintain that junction here, to maintain that continuity of that structure, I would say this would allow some theta 1, this would allow some theta 2 at the hinge, such that point B is finally at its original location and support A has gone up by 1 unit. So this is your profile in this fashion. In this fashion, the profile would be developed. Let's have that one also. So that means up to this point, linear variation, straight line. After that, there is downwards. So this is because of their internal hinge can have different theta from this one, theta 1, theta 2. So we have theta 1 equals to 0. Then from this side, theta 2 some value. So that means as long as load is up to this point, we can have a shear force. We can have a reaction of 1 at all times. On all times when the load was in this part, you would have same value of reaction, that is reaction 1. That means entire load is taken by the support A. That we call it as a parent support. parent support, because this is your dominant support. It takes entire load. If the load is just before that hinge, if the load is at B, we can say directly entire load is taken by that what you call as support B. That's why here the reaction at A has become 0. Then after that, accordingly we can say this one is your simply support beam. If there is some load somewhere here, accordingly the shear force of some we can call it as PB by L would be get transferred, and same would be transferred to the cantilever side. So that's why there is a linear variation decrease, because as long as if the load is towards the point B, support B, more reaction is taken by support B and lesser reaction gets transferred to the this point C, and same amount of that shear force is taken by that reaction at A. So you got the reaction at A. Now you need to get the reaction at B. So based on the thing, this we have only two supports. Can you tell what is the ILD for the reaction at B from this triangle? Can you analyze that? What should be the reaction at B from this analysis? We have only two supports. This is your support B, and this is your support A. Can you tell me what should be the ILD for the what you call as reaction at B? I would say if the load is anywhere, so if we make a load diagram, that if the load is 1 unit anywhere, 1 unit can be anywhere. This is 1 unit of load. This is load. It can have because it is moving load, that we can make the moving diagram that this is the load of 1 unit for the entire thing. But out of that, your reaction at A has taken this amount of load. That means the rest part which you are having, this part would be the ILD for what you can call support B. That means if the load is in this part, if the load is somewhere here, and the value of reaction at B would be in this fashion, I can show that. I can tell that such that the entire value anywhere, such that this part entire thing is 1. This is taking some value, then this is taking some value. Accordingly, this is taking 1 and this part is taking 0. This is taking 1 and this part is taking 0. Okay. Now let's have that now. Let's take that part now. I would say you have some support at B. You remove the support at B, apply unit displacement of 1 upwards. Then after that, the profile formed is your what you call as ILD for that reaction at B. Let's say this is support, this is hinge, this is fixed support, this is point B. You apply a unit displacement of support B. So the profile would be, let's assume there was no support here. So I would say the profile would have been in this fashion. So that's for sure, that profile would be in this fashion. Okay. Now we don't know where it is cutting. Let's assume that it goes in this fashion. Let's assume that it goes in this fashion. Assume that it goes in this fashion. Is it possible? Because support B, you have to ensure that support A is fixed, because support A is fixed, so it should remain intact at its original location. Let's take that. If the support A has remained original at that original location, it can't bend. It can't bend because we don't have any other intermediate section, critical section, so it can't bend. That means there should be some variation of that curved nature. It's not possible. That means the ILD should cut the section at this location, at the hinge location itself. You can also check that using the force equilibrium. If there is some support B, you are applying a shear of V, and we want to say what is the shear force at B, what is the reaction at B. That is 0. For this case, there might be some shear force B, there might be some shear force, but reaction B would be 0 for this case. Similarly, if the load is just anywhere after point C, the reaction at B would be 0. So finally we say this is the variation. It is similar to that of previous problem we had earlier. So that is the variation. We can write this is +1, and it's up to the support C, this is 0. So we can have that in a proper way. I would say this is your reference. I would say this is 1 unit. After that, you go to this point such that this is here is 0 and this is 1 positive. So this is ILD for reaction B. I hope you understand it. I hope you got it. I hope you got it. Now third one is that moment at A. We already saw the moment variation. We already saw the moment variation in one of the problem we take, that if this was your cantilever beam and you applied load anywhere, I said that if the load was here, your moment at A would be 0 because your 1 into 0 equals to 0. So if the load is here, moment here is 0. If the load is at the free end, your moment gets developed, that's maximum. Then after that we say there is a linear variation, that's, so we write this is P into L, or we can write in terms of that 1 unit into L. So this is 1 into L. So maximum moment you can have in this fashion. So that means what you are doing, you are saying because of the moment developed is in this fashion. So but about this point, because of this effect, this is your resisting moment, that moment developed. But the thing is that this one trying to rotate it in this fashion, in the clockwise manner. So that means if you introduce an internal hinge here, you rotate it by theta equals to 1 unit. That means the profile developed is equals to your ILE for moment at A. If this is 1 unit and length is L, this is also L. Now we are going for the similar case that we need to get the moment at A. Let's take that case up to the point C. Let's take that up to the point C. We say if this is your reference line, here the moment would be 0 because if the load is here, that means your what we call as moment developed here would be 0. So how can you draw using Muller Breslau principle, ILD for moment at A? We say you apply unit rotation of at that location in the direction of moment. So because of that P, its effect is in this fashion. So we write P into L, some effect. So we say you apply unit rotation in the same direction of that moment. So we say this would be your profile variation, and it would be up to the point C, because at the point C it would maintain that continuity. You have to ensure that at the support B that it is 0. You have to ensure that at support B your point B is intact at its original location. So it would go up to only point C. It would go only up to point C. We say if you have applied a theta of 1 unit and this is your length of 4, so finally I would say this ordinate would be equals to 4 minus times 4. Can we say that? If the length is 4 up to the point C, the ordinate of that would be 4, and this is unit of 4 meter. We can write this is 4 meter unit. So this is your cantilever. This is your cantilever hinge and what you call as support. Now you're allowed a rotation here. Let's say you allowed a rotation, so you introduce an internal hinge here at this point A. So and there we have also one more internal hinge at point C. Let's say that, and you have to ensure that point B is at the original location, where the internal hinge is that theta A at the internal hinge at point A, and support B should be at the same location. So finally it should be in this fashion. Possibility is that in this fashion the profile would be developed in this fashion. Can we say that if there is some theta developed, it would have been in this fashion. If there was no support at B, but we have to ensure that support B remains at the original location. So support B remains at the original location, and theta can allow independent of each other. So that's your internal hinge at point C. So final profile ILA MB moment at A. This is your profile. So this is your profile. This is your theta, and this won't be theta because this is 3 meter, and there might be some other theta. Okay, we got it. This is your ILE for moment B, moment at A. Now the thing is that, do you have any other problem to go with? Yeah, we have a bigger one. We have a compound beam now. We have a compound beam A, B, C, D. Let's say this is A. After that we have B. After that we have hinge C. We have hinge D. We have support, one more support. After that we have support F. So we need to get reaction A, reaction B, moment G, shear H, moment H. So we need to get ILD for these stress functions. ILD for these stress functions. So what is the location of H? H is at 4 meter from support B. So this is 4 meter, this is also 4 meter. So this is your H. And G is here, 6 meter, 6 meter. 6 meter, 6 meters. This is your H. What you call as G. This is your G, this is your H, and CD, let's say this is E. Now the length is here, we have, this one is 4 meter, this one is 4, after that we have 24 meter CD. After that we have DE equals to 8 meter, then we have 12 meter, this one. This one is your comfort beam. Now for the reaction at A, how can you get that? I would say draw the reference line for the reaction at A, and we say reaction A and reaction B, we can draw that parallelly also, because they are in the simple support beam. They are the supports of a simple support beam from one side and on the other. So we can have the parallel these reactions, ILDs. So this one is your ILD for reaction at A. So let's have that now. If the load is at point A, now we have to go with the Muller Breslau. It says that at the point A, remove the restraint. At the point A, remove the restraint. At the point A, remove the restraint. And in the direction of restraint, offered, apply unit displacement of 1. So this is your 1 unit. This is your 1 unit displacement. After that, what you do? After that, you keep the other supports intact. Now to maintain the continuity at the support C, at the hinge, we say this would be the variation that BC would go down. This is the BC that would go down. But after that, I would say now there is hinge here and there is hinge also at D. So we can have a variation in this fashion. Now after that, I would say there won't be any shear force transferred, and that means after that we have ILD of 0 here. We have already shown you this problem in using that analysis also in the lecture 1 of that ILD. We already saw that if the load was such, let's say load was at support D, at hinge D, load was there 1 unit. I would say, what is the shear force at C? What is the shear force at C? What is the shear force at C? Can you tell me what is the shear force at C? By the moment equilibrium at D equals to 0, you can get shear force C equals to 0. Once shear force is 0 in part C, that means after that point A and point B, they have reaction of 0. So that's what we have here. Similarly, if we take ILD for reaction B, we can have 0 after that. After the point D, we can have a reaction of 0. That means shear ILD would be 0 for reaction A and reaction B after point D. If the load is somewhere here, load is here, you can have a reaction of A and B equals to 0. That means that load gets transferred to which supports? They got transferred to point support E and support F. Because we have symmetric beam, or we can say we have compound beam, it's similar to that. That load was somewhere here. If the load was somewhere here, that was getting transferred to the part AB. Similarly, if the load is somewhere here, that gets transferred to the point E and F. Now we have to see if the load was at point C. I would say if the load was at point C, I would say reaction E and reaction F would be 0, because that C, it's getting transferred to the point this one and this one. Because for this case, if you take loads at C, what is the shear force at D? That would be 0. Accordingly, reaction E and F would be 0. Hope you got it. Okay. Let's have the diagram now. So once we said that at the point A, remove the restraint, and point B, keep that intact. So that is your profile. After that, to maintain that continuity of the structure, BC will go downwards, and after that we would have that rotation up to the point D. So there would have some value. Theta is same. I would say this is the value of that 1/6. Can you say this is for 1/12? This is for the length of 12. 1 unit for the length of 12. and this length is 8, so this is your 8 by 12, that's 0.667. 8 by 12, that's 0.667. 8 by 12 minus times. So if I try to show it by these, we see this was your support A and support B was here. This was your hinge and this was your one more hinge here, and you applied unit displacement. Support B we have to keep intact. Now support C, at the point C, you have to ensure that from the point D is also upwards. So that means the profile would have been in this fashion. Support D, so point D and point B are at the same level. Okay. Similarly, if you want to draw the reaction at F, that would be similar to that of reaction at A. If you try to draw the reaction at ILD for reaction at B, that would be also in this fashion. That would be in this fashion. Let's remove that. Now, if you want to draw ILD for reaction B, I would say remove the restraint, and apply unit displacement of 1 unit at that point, and keep the other supports intact. That means here the reaction is 0. If the load was here at the point A, that means reaction B would have been 0. So this is your variation. Let's say this is unit 1, and after that, to maintain the continuity, I would say, support B is intact. You lifted the support B by 1 unit. This is your support B, this is support A. Now here we have internal hinge, and internal hinge we got that we say BC got upwards, deflected upwards. To maintain the that at point D we have to keep that point D intact at its original location. Let's keep the point D intact at its original location at the level of support A. So this would be your profile. At support B we have a unit of 1, and after that we have at point C maximum ordinate. At point C we have maximum ordinate, and after that we have this profile. Let's make the profile. I would say this would be the variation. The theta would be same. Let's keep this part a little bit upwards. So I would say theta would be same. So this would be variation of that, what you call as reaction at ILD for reaction at B. So this is some unit of 1, and this unit would be equals, this ordinate would be equals to, by the similar triangles, I would say 1 is for the length of 12, and if we have a length of, what is this length equals to? This is 12 plus 8, that's 20. So 20 by 12 we can write. That's 4, that's 3 and 5 by 3. 5 by 3. Is it 5 by 3? I think 5 by 3. I think so. So let's try this one. Let's say we got it. Now third one is that get the moment at G. Now we are going to remove these ones. So moment at G. So we say for the simply support beam we have this one, positive moment diagram. That means this should be the variation, and for this one, if this is clockwise, this one should be anti-clockwise. This should be the variation, and for this one, and you have this anti-clockwise, here it should be clockwise. So finally you are lifting this part clockwise, anti-clockwise in this fashion, such that it goes in this way, and for the other one you are rotating it clockwise such that it goes in this way. So we know that for simply support beam we have that variation. We know that variation is in this fashion. Okay. If we have this one, let's zoom it out. I would say that the diagram would be formed in this fashion. Once you applied that rotation here, theta, I would say there would have some theta 1, theta 2. We have some theta 1, theta 2. So that entire theta, so that total theta, let's say if this is theta 1, this is theta 2, theta 1, theta 2, then finally we can write that theta 1 plus theta 2 equals to 1 unit. Once you rotated that, I would say the ordinate here would be equals to AB by L. AB by L, that is 6 into 6 by 12. That is 36. That's 3. A unit of 3 is here. Ordinate of 3 meter. Ordinate of 3 meter. 3 meter. Then after that, to maintain the continuity of that BC, we say BC would go downwards. Then after that, to maintain the continuity, I would say point D has to remain intact. That means the variation should be in this fashion. After that, there won't be any moment, because we already saw that as long as we already saw that if there is load at D, or just after that D, there is no shear force at C. Once there is no shear force at C, that means no shear and moment gets transferred to the point A, B, anywhere after that point D, B, D, C, B, A. Yeah, online D, C, B, A. We can have that. So this is your variation. After that, there would be a zero variation. There would be a zero variation. Moment at G. This would be your variation. Now, by the similar triangles, can you say what is the value? If this is theta, this is also theta. I would say you have an ordinate of 3 for the length of 6. I would say, and similarly for the length of 4, this is 4 meter. This is no, this is not 4 meter. This is 8 meter. This is 8 meter. This is 8 meter. This is 6 meter. I would say ordinate would be 8 by 6 of 3. That is 24. 4 units negative. Negative 4 would be ordinate here. Negative 4. Negative 4. Here the theta is some value that's same as that of this one. Now the next one is that moment shear at edge. Shear at edge. Let's remove this one, and we need to get shear at edge. Shear force at edge. Shear force at edge. Shear force at edge. Shear force at edge. I would say, let's draw the line. Let's draw the reference line. Shear force at edge. So think of this one as a simple support beam. Think of this one as a simple support beam. And you are saying what is the shear force here? I would say that would be in this fashion. B by L minus times V by L. This one is A by L. Similarly, in this fashion, we can say you have to introduce a slider. You have to introduce a slider here. Once you introduce a slider here, now the thing is that, see the difference. Let's introduce a slider first to get the concept. So we have this one. We have this one. Let's say there we have infinite number of these. We have supports. Infinite number of supports we have. Then we have this point H. If we introduce a slider here, what is going to happen? See, introduce a slider. So for this part, you have to apply shear force downwards. In this part, upward shear force, upward shear. See, so take this section ABH to a side. Take this section ABC to a side. ABC to a side. What is it? Statically determinate or indeterminate? This is statically determinate part of the beam. Statically determinate. You are applying a shear force of V1, and what's going to happen? Would there be curvature developed? What do you think? Do you think that curvature gets developed? I think so. If there is curvature developed, that means ILD would be 0 for this part. ILD would be 0 for this part. If you don't agree, let's make that you don't agree. You don't agree with that. You say that the variation would be in this fashion. Let's make it on the bottom. Let's say this is the variation. You don't agree with that. You don't agree. You assume that this would be the variation. Now, we saw that point B is here. Now, to maintain that, point A has to go upwards. To maintain the slope, point A has to go upwards, but it's not possible. So point A, if you want point A to remain at its location, but your structure is statically determinate, that means there is a curvature developed, and that's valid only for indeterminate beams, because for indeterminate beams, we say that ILD is curved. We draw ILD as curved segments, curved line segments. So that's not true here. So we have to see that now. What is the actual variation? What should be the actual variation? That means the shear V1, it should be equals to 0. Shear V1 should be equals to 0, which implies that upward shear V2 should be a value of 1 unit. That means entire 1 unit should be transferred to the side of H, C, D, E, F. Now let's analyze the H, C, D, E, F. H, C, D, E, F now. You have introduced a slider here. And now the thing that we already saw, if the load was after that point D, there won't be any transfer of the shear forces to either of the point. So we already saw that. We can have that also. We know that this one, keep this one is as your in your heart. Then once the load is at the point D or it's outside the point D, that means the shear force at C is equals to 0. What if the shear force at C is equals to 0? That means shear force at H is also 0, shear force at B is also 0, shear force at A is also 0. If the shear force at H is 0, that means after the point D, the line would be a straight. After the point D, the line would be straight line. That means point D has to remain at its location, and after that ILD would be straight line 0. ILD for shear force at H. So before that, we need to get what should be the variation. We need to get the variation before that. We saw, what do we saw? We already saw that for this part, what you call as A, B, C, what was the ILD? 0 was the ILD up to the point AB, H. Up to the point AB, H, variation was this one, 0. Now we are left with only HCD, SCD, which is having in this some sort of, which is having in this fashion, that this is your HCD. Now you are applying a unit shear of 1 unit shear upwards. 1 unit shear upwards. Let's say that you are applying unit shear of 1 upwards. Unit shear of 1 upwards. So what's going to happen? What do you think? You're applying a unit shear of 1 upwards, and you have to ensure that point D does not go anywhere. What do you think? What should be the profile? Point A has to go up. Point H has to go upwards by 1 unit. You have to ensure that point H goes by 1 unit. You have to ensure that point H goes 1 unit, and support D is at its location. But we say that it is similar to that of that cantilever section. This is very critical problem. Out of these entire, we have this one critical. So we say that if this H goes 1 unit upwards, okay. Now this support D has not to go anywhere. So to join them, we say that the variation would be in this way. We don't say variation would be in this way. We don't say it would be in this fashion. We say shear force would be in this fashion. That means shear force for this part, HSC is same constant value. After that, it goes in this fashion. This is our goal here. This is what we are saying. So this is the variation. Not in this fashion, not some bent shape in this fashion. We say it would be in this fashion. You can verify that if you apply a summation of that free body diagram, summation SFD, whatever you do, you can get the variation as this one. In this fashion. Similar to that of cantilever with an internal hinge. And from this side, it won't go anywhere. That is a proper cantilever from the other side. So it is similar to that of, I can show, this is your cantilever with some internal hinge. After that, you have cantilever, and you want to say because of the what is the reaction for A? I would say reaction at A is in this fashion. This is your A. Similarly for this one, if it goes upwards by 1 unit, because we know that V1 equals to 0, so V2, this is your V2 equals to 1 unit. If this goes 1 unit upwards, after that it would remain straight. Then to maintain that intact condition of D, we say this is your variation. So finally for this part, we have this variation. So this is one of the critical problems we can have from the ILD for this what you call as combined beam. What do we call it as? Combined beam or any other thing? Whatever, this is a bigger beam. So we call it as we say that the variation would be up to the point C in this fashion, 1 unit plus 1. After that, a linear variation. So keep this as a star. This one is a very important problem. After that, you need to say what is the moment at H, moment MH. At the same location, you need to apply that internal hinge. That to get the moment at H, you apply similar to that of you apply this one, such that it goes upwards, it lifts up by some amount. This is clockwise, this is anti-clockwise. If this is clockwise, this should be anti-clockwise. This theta should be in this fashion, and that means in this fashion it should be the theta, and for this one it should be in this fashion. So you are applying at theta 1, theta 2, such that this part goes up in this fashion. So this is your ILD for the BC part. So you can write here value of ordinate would be AB by L. AB by L. AB by L. That is equals to 16 to 2 meter. Is it 2 meter? Is it 2 meter? Why the problem? Is it 2 meter? Okay. We want to see whether this is correct. From the answer we want to see whether this is correct. Have I solved it perfectly or it is wrong? We need to get that now. So I draw this case if this was a simply support beam only. Now you analyze this one. We say you applied a rotation of theta 1 and theta 2 on two different sides. Once you applied on this side, you applied a theta 1, let's say, because there is some moment m1, and you applied from this side some theta 2 because of some moment m2. So we say now analyze this part ABH. Analyze this part ABH. You are applying a moment in this fashion. What do you think? What is going to happen? Some curvature might get developed. So for this part, what you can draw the ILD? How you can draw the ILD for this part? As 0 line, because your curvature gets developed because of that moment. So I can say for this part, you have a 0 up to the point H. That means theta 1 is equals to 0. So entire theta 2 is 1 unit. So you have to rotate that. After that point H, you have to rotate that point H in the what you call as in this fashion, such that you have this point H and you have point C. Now you have this point C. So you rotate this point H, and so points finally you have to ensure that point D does not go anywhere. So finally, profile of ILD for bending moment diagram would be in this fashion. This would be the profile variation. From point H, you rotate theta equals to 1. At the point H, theta equals to 1, because from the other side there won't be any theta provided, because theta 1 should be 0 in order to make sure that that there is no curvature developed in the part ABH, because it is statically determinate, so that theta 1 is 0. So after that, theta 2 would be entirely taken as 1 unit. So finally, if there is point H, you apply theta 2 equals to 1 unit in this fashion. There we have internal hinge at C. That means to ensure that point D is at the same level, this is your variation. So this is your variation. That means this is not correct. You keep that also on the side. You say why this is not correct. It would have been this AB by L corresponding to that, but it's not correct because we have this concept here. You can keep that also inside. And why we are going up to the point D only? Why point D is remains intact? Because of this condition also. This one is critical, and this one is also critical here from this side. So finally, you rotate by some amount of theta equals to 1 unit up to the point C. So this is your theta 2 equals to 1 unit. After that, if the length here is HC equals to 4 meter. If this is 4 meter, what is the ordinate we can have? This is also 4 unit. So after that, you have this point C. Then point D has to remain at its original location. So this is your point D. Then you join them by a straight line. After that, you have a straight, that's 0 ILD. So this is your ILD for moment H, ILD for moment MH. Hope you enjoyed those problems. Let's take the problem number 1 in terms of those values of shear forces and in terms of those loads. Now we are going through the loads. Till now we are going through the unit load. Now we are going through the actual loads. So now we are going to use those ILDs for calculating the moments, shear forces, and reactions. Let's go. Let's take the first problem. That's an easier problem. That's the easier problem we can have from the ILDs. So this is your support A, support B, simply support B. We need to get the, we have some quarter at the quarter span from the left side. There is some section C. Let's say total length of 10 meter is there. That means this part is 10 by 4 and this is 3 by 4 of 10. So we have this section C. We need to get maximum positive shear force. Maximum positive shear force at point C, at section C. If there is a UDL, if there is a UDL of, we say that UDL of, we say that a UDL of 2 kilonewton per meter is acting. We say that a UDL of 2 kilonewton per meter is acting. It can occupy any part of the length, any part of the beam it can take. That means we can have infinite number of length of that UDL. So we need only, but we only need that maximum. We have to ensure that we get maximum shear force. Accordingly, we should fit this UDL anywhere. We can fit it anywhere, but the condition is that we need to get the maximum shear force. So this is your loading 1, and loading 2 is that we have a concentrated load of, point load is also there, point load of 4 kilonewton, and this should be also, it can be anywhere. You can fit it anywhere because they are moving loads. They are not fixed at in a particular location. They can be anywhere, and based on the ILD you draw, you can say where should be those loads located such that we can have a maximum effect of that stress function. Okay, we have one point load, anywhere we can place that, and we have UDL. It has an infinite length. It can be occupied anywhere such that we got, our goal is that we need moment that shear force is positive and it is maximum at point C. So let's have that diagram. Do you know that how it is the shear force diagram of the simply support beam? Introduce a slider. This part goes down, and up the other part goes upwards in this fashion. This is our variation. This is your B by L. This is your A by L minus plus. What is the values we have? This is A by L. This is B by L. So I would say that this is minus. This is 0.25. This is 0.75. Now the thing is that problem is saying get the positive shear force, maximum positive shear force. That means if you're talking about this positive, this is ILD for shear force at C. If you're talking about that, I need positive maximum shear force. That means it's talking about that this area. If the load is only in this part, I can have a maximum effect of that loading. Let's take this. Let's take this part only. Let's take the positive part only to get the maximum positive shear force. I say you have this area with the ordinate of 0.75 and the length of 7.5 meter. Now I would say you place the load entirely for the entire area. You place the UDL for the entire length. You place the load for the entire length, 2 kilonewton per meter. And to make the maximum effect of that point load, where should this point load be placed to have a maximum shear force? Where do you think this 4 kilonewton should be applied such that we have a maximum shear force at point C? If we say you apply load here, we have this point load into some ordinate of 0. So this is 0, negligible effect. So if you place it at the maximum ordinate, P at maximum ordinate, that means it would give me maximum values. V value would be maximum. Is not that true? I think that's true. So let's apply that 4 kilonewton on the top, on the peak ordinate. So this is your P of 4 kilonewton. So how do we calculate that effect total load? We say the ordinate of that shear force diagram is 0.75, but it is unitless. This is some sort of B by L, meter by meter. So it's unitless. To get the shear force is in terms of kilonewton. That means if you multiply that ordinate with that force of P kilonewton into some ordinate of 0.75, you would get a total unit of kilonewton. That's your shear force. Now the thing is that how can you get the shear force out of the UDL and some area is there? I would say if you calculate this ordinate 0.75, this is unitless, okay? there is some length of 7.5 meter, and we have some UDL of 2 kilonewton per meter. That means I need shear force in terms of kilonewton. So if we have some kilonewton per meter UDL, that is W, and if I multiply it with some length of L, and because it's varying, because ordinates is varying, so I can say the average ordinate that is 1 by 2 of 0.75 plus 0. So that's the area. We can say this is the area of the triangle. This is the area of the triangle, and this is some intensity. So finally we write how can you get this problem in this fashion. We say you have this load, you place the load for the entire part of the positive diagram of that shear force at C, and this was your intensity of what you call as 2 kilonewton per meter. 2 kilonewton per meter. So how can we get the final shear force value here? We say this is your positive 2 kilonewton meter. The V positive maximum at the rate of point C would be equal to let's have the effect of point load first. I would say the value of P was equals to 4 kilonewton. I would write 4 kilonewton into ordinate of 0.75 plus area of the UDL, area of the diagram of that ILD between that positive area. I would say 1 by 2 0.75 into length of 7.5 meter into UDL of 2 kilonewton per meter, and you get a value of V positive maximum, that is 8.625 kilonewton. So if you want to write that in a general way, that if you have point load, it's the value of shear would be equals to that point load P into ordinate. And similarly, if you want to get a reaction, maximum reaction, you say what is the maximum ordinate we can have? 1, 0. We say you multiply that one ordinate into that, you place the load at that peak P, so we say P into that ordinate, that will give you reaction maximum. And similarly for the bending moment diagram, from the bending moment diagram, if you have some bending moment diagram, its unit have AB by L, that's in terms of meter. Let's say that is 5 meter. Let's say that value is 5 meter, and we say what should be the point load applied such that we have maximum bending moment at this location, at this section C. If we say, if we apply the same load of P at the maximum ordinate, we can have maximum bending moment of some P kilonewton into 5 meters. That's your maximum bending moment at point C. But if you have UDL, if you have some UDL, so we say that you place partly to the left and partly to the right, such that we have some ordinate here, and we have maximum ordinate at the point C. Then you calculate the total area between these two ordinates. Let's say this is ordinate 1, this is ordinate 2, this is ordinate at C. We write area of that y1 plus yc by 2, and the length here is, let's say this one is your Z. Total UDL length is D, and to the left of section we say there is some Z up to the point we have some side of Z. We write this is your 1 by 2 sum of parallel sides into length of Z. This is your area of that UDL, and you multiply that intensity of W, plus similarly you write that intensity of W into that area from this side. Now you write YC plus Y2 divided by 2 for the length of D minus Z. So this is your I would say this is your intensity of this is your total moment you can have. I would say moment at C, and this is kilonewton per meter, and this is having some unit of meter, and this is also having some unit of meters. Finally you get a unit of kilonewton meter. So we reached here. Let's go for second problem. That's your ILD for, you get reaction at A, reaction B, moment B, shear at G, and moment at G. For these locations you need to get those stress functions, and the beam looks like a compound beam. So as support here, support A, then 3 meter, then we have hinge here, hinge at E, then we have 2 meter. After that we have a support at B, then we have 2 meter, we have a section at G. After that we have 4 meter, then we have a support at C, and we have internal hinge at F, 2 meter from C, then we have 3 meter. After that we have a support at D. So let's go for one by one for these critical points. I would say calculate the ILD for reaction at A. You need to do one thing. What you can do, you release that support and apply unit displacement. You release the support and apply unit displacement. After that, let's say that here this was your support, this was your support, this is support B, this is hinge, and this is support A. You remove the support, apply unit displacement of that point. So the profile should be in this way, but you have to ensure that what you can say, you have to ensure that the point B does not go anywhere. So if this is the profile, I would say there is a possibility that the profile would be formed in this fashion. There's a possibility that profile would be formed in this fashion. So that part we need to check whether the profile is some sort of curved, both the parts have curved nature, or that we can say that it's only in this fashion, that your EB is horizontal and AE is inclined. And after that there won't be any change. Once it reaches to the point B, after that there won't be any ILD, because that after that then we have a curved nature. We want to check that whether our profile is in this way, or want to check whether our profile is in this way, then after that this straight line up to the point B. So for that I think your second case would be the possible answer. So if I take that, I would say let's apply that shear force was just up at point E. If the shear force was at point E, that means if a unit load was at point E, I want to say what is the reaction at A. Can you tell me what is the reaction at A when the load was at point E? I think it was 0. You can treat it as a simply support beam. Load is at the support, so here the reaction would be 0. You apply summation of moments at A equals to 0, and you would get reaction A equals to 0. Now, if at any case you would take any point, any x, such that it's greater than this length L, I would say your reaction at A would be 0 now after that. So I think that second diagram would be correct one. I would go with the second one. I think that the diagram would be formed in this fashion. So there was a 1 unit. After that it goes to 0 in the length of 3 meter. After that there would be a straight line up to the point, up to all points of that E to D. You have that 0 line of ILD, 0 line of ILD. So I would say this is your ILD for reaction at A. And you can still verify that if you apply a load at any section, and you can get the reaction at A equals to 0. Now second case is that reaction at B. Let's take that reaction at B, I would say. Let's write the reaction at B. Let's say this is our reference line. I want that reaction, ILD for reaction at B. So you remove that restraint, you remove that support, So if I remove that support, that means then I apply unit displacement. Let's go for that. I remove that. I apply unit displacement upwards, unit of 1. Let's say it's a unit of 1. So I apply a unit displacement of 1 at that support B. Then after that, what's going to happen? See, we're going with this one. So there is a support C, we have a support at B, and we have a hinge at E, we have a support at A. And we are going to say this was your support at B, this is your support at B. We are going to lift it, we are going to remove that support. this one. But we have support at A and C, but we are going to remove this support at what you call as B. So then after that we lift this 1 unit. When you're going to lift this 1 unit, but you have to ensure that this support, C support, does not go upwards. So that means you have to lift it, okay? You have to lift it, but it does not go anywhere. But how can you lift it? That means there should be some use of internal hinge here. See the hinge at E, if you try to have a rotation here, let's say this in this way. Let's wait. So you have to ensure that your support at A and support at C does not go anywhere. So that means the role of hinge at E would be in this way, that if there is no delta at A, that means A does not go anywhere, okay? That means at the hinge E there would be some change in the theta. So I would say point A has gone, with respect to the reference line, it has gone upwards by 1 unit displacement here, but the point C does not go anywhere. Support C does not go anywhere, and on the same line there would be some support at A that is also not going anywhere. So finally I would say the profile would be in this fashion. There would be some theta 1 from this side of hinge E, and from this side there would be some theta 2, such that the point A and point C are at the same level. They do not vary from their original position. So this should be the profile. That means maximum value of, or maximum ordinate would be at the hinge point. This is your ordinate at the 1. This is your ordinate 1 at the support B, and maximum ordinate we can have this one at the hinge point. So that means you need to join those. You need to join those. So let's join those. I would say support at hinge at that ordinate at hinge would be maximum, and it goes to 0 at the support C. And similarly you have to ensure that support at the support A, it does not go anywhere. So similarly, this is your 0 ordinate. There we have maximum ordinate, we have ordinate of 1, ordinate of 0. So we can calculate those ordinate values. Value of those ordinates, I would say, can you guess what should be the value of this ordinate? I would say, what is the theta here? Can you tell me what is the theta? I would say the value of theta would be equals to, we need to calculate the length between those two supports, B to C. This is your simply support beam BC. You can say your simply support beam BC with a length of 6 meters. So I would write 6 L is equal to 6 meters. So I would write theta equals to 1 by 6. And if I got a ordinate of 1 per length of 6, then accordingly I can write this part is equals to 1 plus ordinate 1 plus 2 by 6, that's 1.33, or we can write 4 by 3. That is ordinate of 4 by 3 here, and this is positive. After that, we want to see there might be continuity at the support C. Once it reaches to the point C, so let's say now where we have reached point C is this one. Point C is this one. Let's say this is the point C. Let's say point C is this one. Okay, this is point C, but it is with respect to the original line at the initial position. That means here the reaction at B is 0. So this is your point C now, and after that there is point C, point F, point support D. So support D is here. That means once your C is on the original line, that means and support D has to also remain at the original line. That means the profile, the hinge has to show that some rotation theta 1, theta 2, such that point C and point D are at the same level or at the original level. So this should be the profile after that, after the point C. This should be the profile. So let's go for that one also. I would say the profile after that would be in this fashion. This should be the profile that is negative, and we can say what is the ordinate here. I would say, what is the ordinate here? I would say the ordinate here, it would be equals to your slope of 1 by 6 and length of 2 meters. So 2 by 6, that's 1 by 3. That's 1 by 3 ordinate, 1 by 3. So this was your ILD for reaction at B. Third one is that ILD for moment at B. What is your B? Yeah. ILD for moment at B. Let's remove this. Let's remove these. Let's remove these. We need ILD for moment at B. We don't need any other thing. ILD for moment at B. ILD for moment at B. So what is your Muller Breslau principle says? What does that say? What does he says? He says that do one thing. You want moment at B, ILD. So you remove that restraint because of moment B. You replace it by what you call as internal hinge. So once you apply internal hinge at point B, this is your point B now. Then after that, you apply theta 1, theta 2, theta 1, theta 2, theta 1, theta 2. Okay, you apply theta 1, theta 2. So let's apply theta 1, theta 2. So let's make a internal hinge here. Let's make internal hinge here. I would say you make theta 1, theta 2 here in this fashion, such that for this part it would be in this way. For this part it would be in this way. For this part it would be in this way, and for the other part it would be in this way. See, if the loading is, let's talk about what should be the direction of that. If you take this point B and the loading is in this side, so a rotation would be in this fashion, or a moment developed would be in this fashion. So in the same way we are going to take that theta 1, and if the load is in this side, I would say the rotation would be in this way. So I would take theta 2 in this fashion. Now we say that we apply theta 1 and we apply theta 2. We need to say whether our theta 1 is having some value and whether our theta 2 is having some value. Let's go take one by one. Let's go for the theta 1. Let's take the theta 1. I think we should take theta 2 first. Then we can finally take theta 1. If I take theta 2, let's talk about only theta 2. So you had a beam, you had some beam, and you are applying some theta 2. Let's say some moment is applied here. Then because of that moment, we said some theta is here. So we have a support here. After that, we have a what you call as internal hinge, and after that we have one more support. Now you are applying, if you apply theta in this part, do you think any curvature gets developed? Because still your structure is statically determinate, and you would see that because of this moment, whenever there is moment, there is a curvature in the beam. Because of that formula 1 by r equals to m by ei equals to d2y by dx2. Whenever there is moment, there is development of curvature. In this part, definitely is there will be a curvature going to develop. So if there is curvature developed in this part because of some theta 2, I would say, bro, let's make the ILD as a 0 line after that point B. So let's make that as 0 line after that point B. Okay, this is your ILD for moment at B. So because of theta 2, your curvature got developed in the beam, which is a statically determinate beam. That means this is not possible. This is not possible for statically determinate beam. So you do one thing, you make a 0 line for that part of the beam. So ILD is 0 for that part. Now for the part 1, you are applying theta 1. Now I would say if the theta 2 is not there, that means no ILD for theta 2. That means theta 2 should have been 0 and theta 1 should be equal to 1 unit total. Now if the theta 1 is equals to 1 unit, I would say you take the beam and you analyze that. Let's say this is that and this is that, and you're applying some moment here. What do you think? Is there a possibility of curvature? Is there any possibility of curvature? If we have a hinge here, let me think that. Let me make the diagram. Let me make the configuration. You're applying moment at this point. We have a support here. We have a hinge here, and you're applying a moment here. Let's say you applied a moment here. You have to ensure that this point does not go anywhere, and there should not be any curvature developed. Let's go for that. I would say I applied a moment here. Now what is going to happen? Is there any curvature in the beam? Because this and this can rotate independently because of this internal hinge. So what we can do? we can rotate this member freely without having any curvature. So this is your profile. I would say this is your profile. Point A is on it at its original location, and you are rotating this part by some theta, anti-clockwise theta1 equals to 1 unit, and finally I would have some shape of this one. This is your ILD. I would say that. Let's go for that ILD now. I would say you rotate it by some theta1 equals to 1 unit, and what is the maximum ordinate we can have then? And I have to ensure that point A does not go anywhere. So your negative BMD has been developed. That means moment at B is negative for all values of X such that load is in this part anywhere. In this part, if the load is anywhere, you would get a negative moment about point B, and that value equals to maximum ordinate we can have. When the load was at hinge E, your maximum moment that has developed on the what you call as point B, on the support B, that equals to what you call as because your theta is 1, this is 2 meter length, so this ordinate is also 2. Why, if you say why at point E your moment at B is maximum, I would say you're applying a 1 unit at E and you have some support of B here, then I would say what should be the reaction at A? Can you tell me what should be the reaction at A? I would say that is equals to 0. That means entire that 1 Newton at the hinge, that gets transferred to the as a share on what you call as on the side EB. If there is 1 unit and it's trying to rotate it in what you call as anti-clockwise, and the moment is 1 into 2 meters, so 2 meter unit is there. 2 meter unit is there anti-clockwise, negative. That's why this is the thing here. We got this ILD. Okay, let's remove this part. Now we need next one. That's what we call as we call that as a moment share at G, VG. We need to get the VGMG. So let's have that VGMG. So we would say that for the VGMG, you do one thing, you apply a slider here. Let's apply the slider here. You apply shear of V1 downwards, V2 upwards. There's some shear of V1 downwards, V2 upwards. So this is your slider. Now, because of the slider, let's take the first case. We would see whether any curvature gets developed. We want to see whether any curvature gets developed. So the first part is that you are applying a shear of V downwards, V1, and there we have some support. We have some what you call as hinge, and after that we have support A. Now let's take this part. We have this point, shear of downwards V1, and we have some support here. We have some hinge here. We have some one more support A. A, E, B, shear. Let's apply shear downwards. If I try to apply shear downwards, that means I should try to move it downwards by some amount. That means this should be the profile. Now there was some support. I had to maintain the support does not go anywhere. I have to make sure that support does not go anywhere. If I apply that shear of V downwards, that means it's trying to rotate it in this way. It is trying to rotate it in this way. Had there not been any what you call as internal hinge, if this was in this fashion, statically determined beam, you apply like a load of V1, that means it would definitely going to have a curvature developed. It's going to definitely having to go for a curvature of that curvature is going to develop for this case. But because there is some internal hinge, it would allow that rotation to happen such that point A does not go anywhere. See, if this point, if the support is here, support B is here, you're applying a shear of V downwards, your point at hinge goes upwards, and if you want to take that point A does not go anywhere, I would say let's have that hinge connection here. So the profile would be in this fashion. profile would be in this fashion, such that your support B is here, and this is your hinge connection, and support A is here, and this we have that shear of V1 downwards. So I can draw that diagram now. I can draw this diagram. So let's make that diagram now. I would say you are applying some shear of V1 downwards, shear force of V1 downwards. Then after that, the profile looks like in this fashion up to the point E. Then after that, to maintain that, point A does not go anywhere. So this is your connection. This is your part one. Now second one is that let's talk about this part. You're applying a shear. So you're applying a shear of V1 in this point upwards, and we have some support at C. Let's say this is our support C. We have some hinge at F, and we have support D. Now we are doing one thing that you apply shear of V upwards. So what's going to happen at the point B? Point C does not go anywhere. So the profile would be in this fashion. Now support D, you have to ensure that this support C and support D are at the same level. So that means the theta 1, theta 2 developed at the that hinge F should be such that the point C and point D are at the same level. So this one. So this should be the profile. That means this is a parallel line cutting that reference line at point C, and after that we have this connection up to the point D. This is the profile. That means your GC that's above the reference line. That means GC is above the reference line. After that we go to the point F with the same slope. Then after that we connect it with that point D, such that point D is at the initial position. Then after that we can join this part also. Let's join this part also. I would say this is the variation. So this is your ILD for shear force at G. ILD for shear force at G. Now we need to get the values. I would say, can you get the value here? I know the values also. I would say the value here would be equals to, that is, if I take this as a length of 6 meter, if this is a length of 6 meter, L is equal to 6 meter. I would say there's some shear of 1 by 6, and this part is equals to 2 by 6. That's A by L, 1 by 3, and this one should be equals to 2 by 3. That's 4 by 6. If I go from this side to this side, I would have a similar triangle that the slope here is also 1 by 6. That we can see later also. So this is your B by L, A by L. You can get the ordinates also, and by the similar triangles you can calculate this one also. This one is also 1 by 3, and from the other side, ordinate is equals to 1 by 3. Let me show you how this 1 by 3 has here. So I would say ordinate here is 1 by 3. How that is possible here? I would say you have from the similar triangles, you have this ordinate of 1 by 3 for the 2 meter, and slope is same, and this ordinate for the 2 meter is also having same ordinate, because slope is same, length is same 2, so ordinate is also same 1 by 3. Now the final part of this problem is that you need to get the shear moment, ILD for moment at G, 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 mg. Now for that you have to apply an internal hinge here. You apply internal hinge here if you want to see whether there is curvature developed in the two parts. Whether there is curvature developed in the two parts. Think it of as a simply support beam. Then we know the simply support beam goes in this fashion. This was some theta 1, and there we have some theta 2. Similarly, you have to apply that theta 1, some theta 2, such that theta 1 plus theta 2 equals to 1 unit rotation. So from that, I would say that the profile would be in this fashion. Let me show you whether there is any curvature developed or not. Let's talk about the first case. That's your AE, B, and G. AE, B, G. This is your G. This is your B. There is some support. Yeah. A, E, B, G. A, E, B, G. Then apply a what you call as this kind of rotation, what you call as anti-clockwise. So if I apply anti-clockwise rotation, that means this part is going to, if this is your support B, if you apply anti-clockwise rotation, that means profile would be in this way. So this should be the profile, but you have to ensure that support A does not go anywhere. So if this is possible, that if the bend, if there is no curvature developed, and I can have that point A on its original location, that means there should be use of internal hinge somewhere. So I got this profile now. I got this profile. So point B is at its original location, but point G has gone upwards, and your hinge has gone down with respect to point B, and support A is at the level of B. So this is your profile. Let's make this profile. That means this is possible. There is no curvature developed, so the theta 1 would be there. Theta 1 would be there. So let's have that ILD for this part. Let's have the ILD for this part. I would say support B does not go anywhere, but your G goes upwards, and your E goes downwards, and after that you have to ensure that A does not go anywhere. So this is your profile. So I would say this ordinate, I know this value. This value is equals to AB by L. AB by L, that is 2 into 4 by 6. That's 8 by 6. 4 by 3. That's 4 by 3 we can write. This ordinate is positive 4 by 3. And similarly from the other side also, because of that symmetry of those supports and hinges, we have hinges and supports, but length is different, but that does not matter. So we can get the ordinates. So it's similar to that of this first case. You can do that also. So I would say at the support C, you have to ensure that it does not go anywhere. On the similar grounds, I would say support C does not go anywhere, and to maintain that continuity of that member GCF, that F has to go downwards, and after that you have to ensure that D does not go anywhere. So this should be our profile. So I have to make sure that this part is not there. This is your point D here. This is not there. Then I would say I got this 4 by 3 for the length of what you call as 2 meter, and if this is also 2 meter, that means this is also 4 by 3 negative, because theta is same. Now if this is what you call as 4 meter and this is only 2 meter, I can say by the symmetry of that triangles, I would say this one should be equals to 2 by 3 negative. So this is your ILD for moment at G. Now let's take the problem that we can have. Let's take a beautiful problem now. Let's go for the problems. Let's take the problems now. The problem is saying that you need to get the shear force at C. Yeah, we can say ILD and bending moment at C. Shear force at C, bending moment at C. You need to get these two values for the simply support beam with the loading as given in this fashion. I think we should take simpler problem first. Should we? We should take a simpler problem first. Then after that we can go for this problem. Let's keep it on a side. I would say let's go for a simpler problem first. Let's take the problem that is simpler problem. It's saying that the maximum positive bending moment at D, you need to get the positive bending moment at D. What should be the maximum value of positive bending moment at D for these loads? We have a moving load of 4 kilonewton. Moving load of 4 kilonewton. Yeah, a moving load of 4 kilonewton point load, and moving UDL of what you call as 300 Newton per meter. And we have a self weight also. Self weight does not go anywhere. Self weight is for the entire structure. Self weight of 200 Newton per meter. Then we have a beam of, the beam is in this fashion, that the beam looks like in this fashion. So we say you have support A, then after that 5 meter, after that we have hinge at B, after that we have 5 meter, after that we have one more support at C, after that we have 5 meter, after that we have 10 meter. So we have some support, we have some section at D. So this is your section at D, and this is your E. We need to calculate what should be the maximum positive bending moment at D. Now for that, if you draw ILD, then I can say where should be those loads placed such that we can get maximum moment at D, positive bending moment at D. Can you draw the ILD for this problem? Can you draw the ILD for this problem? You can think of this part as a simply support beam. After that, you see whether there is any curvature developed. Then after that, you can draw for this case also. So let's apply some theta1, theta2. If you apply some theta1, theta2 for this case, it looks like a simply support beam. I would say the ILD would look like in this fashion. I would say the profile would be in this fashion. And to maintain the continuity, there would be allowed, the theta would be allowed at B such that support A does not go anywhere. This should be the profile. And the value here would be AB by L. AB by L. AB by L. AB by L. Your L is 15, A is 5, 10 is B. So 50 by 15. That is 3.33. And this is unit of meter. And by the similar triangles, can you get this value? I would say this is for the 5 meter, and similarly this is also 5 meter, and you would have ordinate same value of ordinate here also, because this is 5 meter and this is also 5 meter. So ordinate of 3.33 meter also here. Now the problem is not saying that anywhere, it's saying that maximum positive bending moment, If it's talking about positive bending moment, that means the moving load should be placed only on the positive side. Only on this side, the moving load should be placed. So if I place the UDL for the entire length on the positive side, I would get positive bending moment at bending moment at D. Positive bending moment at D. For positive bending moment at D, place the loads. Place loads only in positive side. If you kept those loads in the negative side, that means they have to be subtracted so that the net value would be lesser. So you need to keep the loads only on the what you call as positive side of that ILD. If this is your ILD for moment at D, that means you have to ensure that loads are placed after the support C. That means if the loads are in this side, it would create negative moment about point D. That's why your negative side is there. So you have to ensure that loads are in the after the support C, after the point E. So this was your, we can call it, this one is a moving UDL. I can have the value as 300 Newton per meter. And for the effect of that concentrated moment, load that is 4000 Newton, what should be displaced for maximum positive bending moment? Should we place it on this ordinate, or should we place it on this ordinate, or anywhere other location? I think for positive bending moment, it should be placed on positive side, and that too on the maximum ordinate itself. If I place it on the maximum ordinate itself, let's have that value. Let's have that ordinate. I would say I'm going to place it here. If I place it here, that load. If I place that load here, that load of what you have, 4000 Newton. 4000 Newton. If this load was 4 kilonewton acting at the ordinate of this one, this is your ordinate, maximum ordinate of 3.33. But one thing is we are missing something. We are missing the self weight itself. Now, talking about the self weight, how can you show the self weight now? Self weight, you have to ensure that self weight, we take the entire length of the beam for the self weight, because self weight is not moving. It's every member, every part of the section, every section is having some weight, every length is having some weight. That means each of the length segment we have to encounter in order to get the maximum positive moment. That means UDL is placed on the entire length. If I place that UDL for the entire length, so this is your UDL of what you have, 200. That UDL of 200 Newton per meter. You can't skip that UDL of self weight. You have to ensure that it's on the entire length. But this one, moving load, it's provided that you can have these anywhere. You can place them anywhere because they are moving. We can fit them anywhere. And UDL is also moving. You can have its length, any part of that length. If it is needed that you take the UDL for the entire length, then I can take for the entire length. If it's needed for you take only for the particular length, I can take it for the particular length, because you can have that it's given that your UDL is infinite. Moving UDL can have length greater than the span total span length. Its length is greater than the total span length, so we can use that. That means let's assume that the moving load is some sort of moving from left to right in such a way that the rest of that UDL is somewhere outside the beam, such that only we are keeping that UDL, this part, live load. Do you got it? So it's up to us. We only need maximum positive bending moment. For that, we are keeping only on the positive side of that beam, such that to get the positive bending moment value. So let's write that now using those calculations. I would say positive bending moment at what you have point D is equals to, what is the maximum ordinate we can have? 3.33 into UDL load of, I would say 3.33 meter into load of 4 kilonewton. This is your first effect. Second effect is that area of the UDL, that area of the loading diagram, positive loading diagram. I can take this one. Area of the positive loading diagram. I would say area of the positive loading diagram is 1 by 2, maximum ordinate of 3.33 meter into length of, what is this length? I need to see what is this length equals to. That is 15 meter. And on this loading, this is area of the ILD between these 2 points, and I want to see what is the intensity we can have here. See, we have two UDL here acting. One is your self weight, and next one is that moving load. One is having a intensity of 300 Newton per meter. Next one is having intensity of 200 Newton per meter. This is your moving load. This is your self. Then after that, this was your positive values of moment, and we have one more effect, that is negative moment. So I can write that also, minus 1 by 2, area of that diagram 1 by 2 into your ordinate of 3.33 meter into length of 10 meter between A and C, 10 meter. Then you multiply with the intensity of that UDL, that's 200 Newton per meter self weight. 200 Newton per meter self weight, and you can have that maximum value of bending moment, that is equals to 22.5 kilonewton meter. This is the approach we can have in the ILD. You can also solve this problem. You can also solve this problem by the concept of simple those SFD BMD. If I want maximum bending moment at support D, I would say you have a UDL for the entire length. You have the UDL for the entire length with the intensity of 200 Newton per meter as a self weight. After that, you have some UDL acting for the positive side. That's equal to 300 Newton per meter. After that, if you want maximum moment at the point D, you apply concentrated moment at the point D itself. Concentrated load, sorry. You apply that concentrated 4 kilonewton at the support itself. Then after that you do one thing. You calculate the reactions and apply that summation of moments about that point D. So once you calculate the reactions, so let's say the reactions was your 500 Newton. You had some reaction here also. You had some reaction here equals to 4750 Newton. And after that, if you calculate that we have some reaction here, I need to calculate moments, summation of moments at this point. Let's say the moment here is empty, and we have some load here acting. We have some UDL also, that is 500 Newton per meter for this length of 10 meter, and we have some upward reaction of 4750. We have some reaction of 4750 Newton. Then we can apply summation of moments at D. We can also get that 4750 into 10 minus 500 acting for 10 square by 2. So you can get the value of 22500 Newton meter, similar to 22.5 kilonewton meter. 22.5 kilonewton meter. Let's take the second problem we had. Initially we had we said that we are going for this problem. Shear at C, bending moment at C, simply support beam. This is support A, 4 meter your section C is here at 4 meters. I would say if this is 2 meter, after that we have a loading of vertical loading of 40 kilonewton. Then after that we had a UDL of 10 kilonewton per meter for a length of 4 meter. After that we have 2 meters. Then after that we have a UDL of 60 kilonewton. After that we have 2 meters. After that we have 80 kilonewton. After that we have 4 meter and simply support beam. So this is your roller support at B. Now there is the section C is at this point, that means at 4 meter from support A, section C. So on this section we need to get the shear force and bending moment. So if I talk about shear force, can you draw the shear force diagram? I would say, can you draw the ILD for shear force at C? Since your beam is symmetric, yeah, simply support beam, I would say the diagram looks like in this fashion. Let's have that straight line. I would say the variation would be in this fashion. For the first part, you have to go up downward shear, and in the next case you have to go upward shear. And simply support beam, there is simply support beam, you have to just lift those, but then after that join by straight line. So this ordinate, we can say this is your, what is the total length we can have? That's 2 plus 4 plus 2 plus 2 plus 4, total length of 6 plus 8 plus 14, so length of 14, and this ordinate would be equals to, yeah, where we are left, total ordinate of 14, yeah, length of 14. Then this ordinate is equals to, this is your A, the value of A is equals to 4, and this is your value of B, so value of A is equals to 4 meter, because section C is at 4 meter from A. So I would write minus A by L, that is 2 by 7 negative, and this is positive, and this one would be for your 10 by 14, that is 5 by 7, such that overall value of 5 by 7 plus 2 by 7 is equals to 1 unit shear. So you got this one. Okay, now but the loads are fixed for this case. For this problem, loads are fixed. Now we have fixed the load condition. Loads are fixed, I would say loads are fixed. So this is your case that loads are fixed. And now we need to say what is the maximum shear force at C and what's the maximum moment at bending moment at C. Now I would say for this loading, let's have those dash lines also. Let's have those dash lines also to get understanding. I would say at this point there might be some intensity, there might be some ordinate, and on this point there might be some ordinate. At this point there might be some ordinate. At this point there might be some ordinate. We need to get those ordinates, then you multiply them to get the maximum values. I would say this is for the shear force, ILD for shear force at C. Now there are two possibilities. One is your negative, shear can be negative and it can be positive. Now we can have that maximum shear in negative maximum shear force and negative positive maximum shear force at point C. So we need to calculate those. If we calculate negative shear force, that would be lesser because you have only one of the loads acting here, and intensity is also lesser. Intensity of that load is also lesser. If I calculate that effect of negative, if I calculate only shear force, negative shear force, then we have one problem. If I calculate only one shear force positive, then we have one more problem. But if I take general, if the problem is saying that you solve for the shear force at C, you solve for the shear force at C, that's talking about general value. That means you calculate for the entire part, the entire value you can have, net value you can have VC. So you need to take all those loads, all those effects together, such that you can get value of VC. So let's get the ordinates. If let's say this is 2 meter, this is 2 meter, and this is 2 meter, this is 2 meter, this is 2 meter, this is 4 meter. Now I would say that what should be the ordinate here? What should be the ordinate we can have here? I would say by the symmetry this should be 1 by 7. This should be 1 by 7, can I say? And if this is 5 by 7 for the length of 10 meter, that means for the length of what you can have 8 meter, it would be, this part would be 5 by 7, 8 by 10, and this one would be 5 by 7, 6 by 10. This would be 5 by 7 and 4 by 10, 5 by 7, 4 by 10, and you got these ordinates. That means 5 ones are 5 twos are 2 twos are 2 by 7. This is equals to 2 by 7. Similarly, you have these ordinates 3 by 7, and this is 4 by 7, and finally that one is 5 by 7. 2 by 7, 3 by 7, 5 by 7, 5 by 7. Yeah, 4 by 7, 3 by 7, 2 by 7, 5 by 7. Okay. Now, to calculate the shear force at this location of C, you would say, what is the shear force at C? I would write VC is equals to, I would say, I would take the positive values first. Let's calculate from this side. I would say this value into 80 kilonewton. So I would say 80 kilonewton into ordinate of 2 by 7 plus second load is 60 kilonewton into ordinate of 3 by 7 plus third load is there. It is a UDL. It's a UDL. Now I need to take the for the UDL I have to take the area under the curve. Area under the curve. I would say 1 by 2 sum of parallel sides 5 by 7 plus 4 by 7 and sum of parallel sides into length of 2 meter. Your length is 2 meter. Area for that area of that trapezium 2 meter. And after that you have to multiply the intensity of 10 kilonewton per meter. And these all values are positive values. Then I have to subtract that negative value of area of that diagram. This one is your negative area. I would say 1 by 2 sum of parallel sides. One is your 2 by 7. Next one is that 1 by 7. And length of, what is the length we have? 2 meter. After that, intensity of 10 kilonewton per meter. Then we have one more negative value of 40 kilonewton. 40 kilonewton acting for at the ordinate of 1 by 7. So we need to calculate that value. VC equals to, total V equals to 51.43 kilonewton. This is your shear at C. This is your general shear at C. It's not talking about whether it's positive or negative. It's talking about that what is the shear at C. Other problems, sometimes we say, what is the negative shear? What is the maximum positive shear we can have? Then at that time we have to only take those separate diagrams also. Separate diagrams. Now we got this. Now second one is that moment at C. Now second one is that you need to get moment at C. Moment at C. Let's remove this all stuff. In these ILDs you have to just do that similar triangles. You have to do similar triangles. This just you have to understand. You have to understand the concept, and after that it's all calculations. Now second one is that ILD for moment at C. Do you know that what is the ILD looks like if you have a simply support beam and section is somewhere at some section C? We know that value equals to AB by L. So the diagram would be in this fashion. So this would be your that would have ILD for bending moment at ILD for moment at C. This ordinate would be equals to AB by L. AB by L. Value of A is 4 meter and B is 10 meter and divided by L. 40 by 14. 40 by 14, that is 20 by 7. Let's have this ordinate 20 by 7. Let's call it as YC. Ordinate at C. YC. Ordinate at C. Now we have these loads also acting. So from this side, here we have some load of 40. After that, UDL of 10 kilonewton for 4 meters. After that, we have here 60. After that, we have 80 here. We need to get those ordinates also. Ordinates. I would say the ordinate here would be, so this one is your B length. This is 10 meter, and this would be 6 meter. Twofold. This is 4 4s are 8 plus 2 10, and this is the length of 10 meter, and your 60 kilonewton load is acting at I would say for the triangle of 6 meter. For this 6 meter triangle, your 60 kilonewton is there. So for this 6 meter triangle, our ordinate would be 20 by 7 for the length of 10. I need for the length of 6, and this ordinate would be 20 by 7, and this was for the length of 10. I need for the length of 4 meter triangle. So we got these ordinates, and units would be in the form of meter, and after that we have this area under the UDL. So we need to calculate these ordinates also. I would say this value would be equals to 20 by 7, 8 by 20. Can I say that? 8 by 10. I have this value 20 by 7, 8 by 10. And from this side, I would say total length was equals to 4 meter was this one. This was your 4 meter. Let's forget this one. This was your 4 meter. And for the 4 meter, we have 20 by 7. And for 2 meter, we have 10 by 7. We got these ordinates now. We can say what is the moment at bending moment at C. That would be equals to those ordinates into loads. Let's go for this one. I would say 10 by 7 ordinate. It's having a unit of meter, and multiply that 40 kilonewton meter. 40 kilonewton plus. Then you keep the UDL for now as it is. Let's go for the 60 kilonewton. 60 kilonewton into ordinate of 6 by 10 into 20 by 7 meter, and plus similarly third load is the 80 kilonewton. Then we have 20 by 7 into 4 by 10 meter. Then after that we have that area under the UDL. One is your this triangle, then trapezium, then we have second trapezium. So for the first trapezium, I would write 1 by 2, that is 10 by 7 plus parallel side, sum of parallel sides. I would say plus 20 by 7, and length is 2 meter. We have 2 meter, and this one is also 2 meter plus plus. As the loading is same, we can keep that common. I would say 1 by 2. Then we have 20 by 7. Then we have this ordinate of 20 by 7 for the length of 8 by 10, and we have to multiply that 2 meter. After that, we had for the entire thing, we have to multiply that intensity of 10 kilonewton meter. 10 kilonewton per meter for the entire part of this one. So this is your what you call as bending moment calculations. So you can get the value as equals to 345.71 kilonewton meter. So hope you enjoyed that part of the problem also. And this was the end of this lecture 2, and now lecture 3 would be going for the maximum values of SFD, BMD, SFD, shear force, and bending moment. And absolute, we call them as absolute moments also. In the next lecture, we'll be dealing with that. Thank you for watching our series of ILD. Thank you.